Hello, and excuse me. Welcome to OARC 34, our first virtual OARC workshop of 2021. Before we start proceedings, I would just like to run you through a few pieces of information, and then also for those of you who it's your first OARC workshop, I have a few things about a little introduction to OARC to share with you, and then we get on with the workshop proceedings proper. My name is Keith Mitchell. I'm DNS OARC president. I'd just like to remind you all, this is an online event. For both online and offline events, OARC has a conduct policy. OARC members are bound by this, and you also agreed to adhere to this policy when you signed up. So if you have any concerns about behavior or conduct during the workshop, please let us know. The workshop is being recorded, and the talks will be available on the OARC YouTube channel after the event. Because it's a webinar, all non-speakers are default muted during the event. It will only be the speakers and the panelists and people who are asking questions who will have their audio turned on. I see that we have about 160 people attending, so that's great. All event times are in universal coordinated time, and the social media hashtags that we're using are LoveDNS and OARC34. For meeting interaction, which is not question and answers with the speakers, we're using our Mattermost chat platform, which we migrated to last year, previously using Jabber. This is an open source cross platform, provider neutral, so you can use it from browser. You should be able to get a client for most platforms. If you didn't already sign up, we recommend that you do. You can do that at chat.dnsoarc.net, and we will be using the workshops community channel for general discussion. But we'll not be monitoring that for questions to the speakers or operational comments about the operation of the workshop. And you can get the clients at mattermost.com. Questions and answers. Each speaker slot includes 5 to 10 minutes at the end for questions and answers. If you want to raise your question, if you want to speak your question, we're doing it 2 ways this time. Previously, we've only done it with typing questions. This time you can speak your question as well. So if you wish to speak your question, then use the Zoom raise hand facility. You then need to wait for the session chair to unmute you, and then once you accept that, you can proceed and ask your question. If you prefer to type your question, use the Zoom question and answer panel, and it will be read out by the session chair. And obviously this is as close as we can get to first time, first serve, and time permitting. Most of the speakers will be available in the Mattermost channel and or at the social event if you have questions to ask that there isn't time for. And as every one of these workshops, for the benefit of all the remote people, please identify yourself and your affiliation when asking. We'd like to get presentation feedback. We're experimenting with doing this a different way this time. We're going to use Zoom polls in real time, and that's the only way that you'll be able to rate speaker presentations and content. These will be displayed during the question and answer period, so you've got maybe 5 minutes to give your feedback. Please vote by clicking on the relevant panel, which will pop up. We gather that data, we compare it to the scores that the program committee have for the presentations during their review process, and that helps us keep on track and have the content that you like and guide the program committee. There's also a general event feedback survey about event logistics and how things ran and what your experience was like. We like feedback on that as well. You can complete that at any point during or after the workshop. We'll be running a social event. The social room will be open during the 2 long 1-hour breaks on each day, and also for an hour after today's proceedings. There's the Zoom room. We'll share the password shortly. And OARC 34 restarts at 1600 UTC Friday, and reuse the same workshop link, not the social link, the workshop link that you got and used for today. So that basically covers the meeting logistics. I'd like now to just run through a few things about OARC for those of you who are not already members, or for those of you for whom this is your first workshop. Of course, at this point in a room full workshop, I'd be able to look out and all the new people would be able to have, you know, their green badge tags or whatever, and I'd be able to say welcome. Well, welcome anyway. I hope that we'll be able to see you at a physical workshop at some point before too long. But in the meantime, a little bit about OARC for those of you who are not familiar. What is our mission? It's about making the DNS and the internet work better from an operational point of view. To do that by bridging with the research community and focusing on data collection, analysis, scientific method for running the internet, to provide useful services and tools to those of you who are running the DNS. It's about relationship building, and it's about sharing information responsibly. It's about enabling knowledge transfer by organizing open workshops and increasing the public's awareness of the DNS significance. We have a wide member community, which includes many providers, DNS operators, CCTLD and GTLD operators, vendors of open software. We have over 100 members, and it is a very diverse community. Our technical resources, we have a data catalog, which we've been gathering for over 15 years now, over 250 terabytes there. That has needed some love over the past year, so we're currently upgrading our main infrastructure in Fremont, California to support that. We have a very wide catalog of open source DNS tool software. Jerry is available during the workshop if you want to ask him as our chief developer. We have a suite of active DNS test services. Again, we've updated one of these recently, and we have some secondary sites in Ottawa and Stockholm to complement our infrastructure. If you want to become a member, there are a wide range of categories, from supporter all the way up to diamond. The two lowest categories have some restrictions on them. If you're a supporter, then we expect you to contribute back to OARC in some kind, maybe by providing data uploads or presenting at a workshop or a peer-reviewed journal. And the blue category is for small organizations and individuals only. Please contact Sue Graves, who again is present throughout the workshop if you're interested in becoming an OARC member. OARC governance, we're an independent legal entity, membership organization with a diverse member base. We're financially self-supporting. Despite the pandemic, we've been doing quite well on that recently. We have best practice self-governance. We try to be as neutral as possible in the field. Our board is elected by the members. There are 6 executive staff who are all part-time contractors. We have an awesome volunteer workshop program committee. If you think this is a good content, then you have them to thank for that. They've been working hard for this one. And we have official non-profit status in the US. At OARC 33, we had our first virtual AGM and our first fully online board elections. We only had one change to the board composition. I'd like to welcome Joe Abley from PIR as our newest director. And again, I believe most of our board members are present throughout the workshop. Here's the team. As you can see, we're based somewhat geographically diversely. So remote working is what we've been doing since long before the pandemic, and we're keeping that up. Here's the program committee. I'd like to welcome several new members. We did quite a changing of the guard at the program committee. Pallavi Ras from Salesforce, Manuel Bertel from Facebook, Brett Carr from Nominet, and Willem Turp from LLNet Labs. And also like to thank Jan Vlečak from NS1 from taking over the chair role. And again, all the program committee members have worked hard for this workshop and are present. Our next workshops, here's the plan. OARC 35 will be doing basically the same format as this workshop, May the 6th to the 7th. It will be 1.5 to 2 days long. Depending on the amount of content, it will be fully online, and we've just opened the call for presentations. So if you're interested in talking, then we'd love to have your submission. The board decided that we will not do any physical workshops during Q1 and Q3 this year. So the provisional plan for 2021 is that we'll probably do some kind of short OARC 35A event during the summer. The AGM, we may do that in October. There might be a possibility for having that as a hybrid physical event. We have OARC 36 co-located. The plan is if we have a physical OARC 36, then we would co-locate that with RIPE 83 in November. If RIPE 83 is a virtual meeting, then it's likely that OARC 36 will be as well. And then we have committed to a physical workshop in a year's time on 37 in Austin, Texas, co-located with Nanog, which I hope that we'll be able to see everyone there. Quick, here's what we've achieved recently. As I said, we made a major investment in our data store. That's being commissioned at the moment. I'm pleased, thank you for everyone that made a donation to make that possible. We also received grants from Comcast and Mozilla to add DOH capability to our DNS perf testing tool. We had a grant from Aaron, and we pretty much completed the work on that, to add RPKI origin validation to our Check My DNS tool. We recently did some updates to DNSViz in terms of encryption support and the server platform. And I think the other thing that we've achieved over the past year, and we wouldn't have done it without the support of our community and the hard work of our team, is operational continuity and a successful transition to online events despite all the pandemic and everything else that's been going on. So why become an OARC member? I'm not going to oversell this, but we believe that this is a unique community. If you become a member, you can help influence the tools and services that we do. You have access to our data set and the ability to share and analyze that. We have a whole bunch of community coordination resources to respond to incidents and threats. For example, we have a presentation about a vulnerability for members only tomorrow. And we're a neutral party. We're a non-profit, we're a membership organization. We're free of vested interests in the DNS space. And there is, in the words of our own members. Anyway, I've said enough. You came here for technical meat and not just what's going on with OARC. So with that, I will hand you over to session chair for the first session, which is Brett Carr from Nominet, and also Willem Turk from LNet Labs will be the question and answer monitor. So over to you, Brett.
Thanks, Keith. And on behalf of the Programme Committee, welcome to OARC 34. As usual, we have a packed agenda of interesting talks which should keep you entertained and informed over the next few hours. As already mentioned, if you've got any questions at the end of each presentation, you can either add them to the QA box in Zoom and I'll read them out on your behalf, or raise your hand and I'll allow yourself to unmute yourself to ask the question directly. Lastly, from me, before we move on, you'll see a survey pop up after each talk. If you can answer the questions when you see them, this really helps the Programme Committee shape the future content to your needs. Right, without further ado, I will hand over to an old friend of DNS OARC. Geoff Huston is going to give us tell us about his analysis of DNS Flag Day from last year. Over to you, Geoff.
Thanks a lot, Brett. Let me share my screen. And hopefully everyone can see that. So we good, Brett?
Yeah, no problem. Presentation is fine, and we can hear you well now and clear.
Fantastic. Well, welcome to this weird dark void I am still inhabiting a year later. Yes, it's still 3 in the morning. Yes, there's only me here. But if any of you are out there, good morning to you too. Look, it's a pleasure to be here, and a pleasure to talk about some of the work we did at the end of last year. Right inside that DNS OARC mission of analysis and measurement. And in this case, what we're looking at is a recent event, the DNS Flag Day 2020. There's a screen snap. And it was recommending a couple of things. If you ran an authoritative DNS server, you should have configured your server not to accept eDNS buffer sizes that were sent to you over queries, not accept them if they're larger than 1232 bytes. And you're basically meant to down negotiate to that value, and don't send larger answers if you're authoritative. And for recursive resolvers and even stub resolvers, the guidance was you really should be configuring down low, and again, 1232 bytes. There's an interesting footnote there, and I'll just comment on this for a second. you must resend your query over TCP if you receive a truncated UDP response. Well, not quite. If you get the answer you're looking for inside the truncated response, you are allowed to press on. Whether you should or shouldn't, who knows? But you're certainly allowed to use what you get if what you get is okay. So truncation doesn't necessarily force TCP. Anyway, I digress. The exact date, 1st of October, all gone anyway. 2 questions in all of this. What happened? Did it work? Was it a flag day? And what about that recommended value of 1232? It seems such an odd value. It's related to a V6 value of the minimum unfragmented packet in a V6 network of 1280 octets. And then if you take away the IPv6 header and the UDP header, you get at 1232, but that's only a V6 setting. It seems quite small. Too small? Too large. So let's just have a look at what happened here. Here is the first 8 months of 2020. And what I've done inside this is actually taken the data coming from our measurement work at APNIC Labs, work done, by the way, with Joao Damas. Thank you, Joao. I've taken the first 8 months of 2020 and basically just plotted the relative incidence of buffer sizes that I see in incoming queries. And there is no doubt that the EDNS RFC, someone remembers the number, 6891 comes to mind, but it's early in the morning and God knows that's just a number. Most folk took that to heart, and up around 80 to 95% of queries came in with an EDNF0 buffer size big, 4096. The next most popular was none at all, 512, and then various sizes below that. Interestingly, there's a big difference between weekday and weekend. In other words, there's a big difference between enterprise and retail ISP, where 4096 is more prevalent on weekdays, sorry, more prevalent on weekends, ISP, and less prevalent on weekdays inside the enterprise. And, you know, what we find with 512 is almost the opposite. Enterprise is, I suppose, more prone to using no EDNS0 buffer size than the weekend. Flag Day, was anyone paying attention? Sort of. Were we paying attention within a month or two? Oh yes, no, we got it. And what we found is that 4096 dropped from 84% to 70%, and some other sizes came up. You'll see in the orange down the bottom of the screen here that we saw the rise, oddly enough, of a range, some value between, 1440 or thereabouts, or 1400. So let's just divide this into 2. The buffer size greater than the MTU, fragmentation is okay. Send me big packets, I can cope, says the querier. Fragmentation is not allowed. The buffer size is less than the MTU. And what we actually found, if you look at it that way, was that fragmentation is okay, dropped as a signal from around 85% down to around 75% by December. So in the terms of the size of the DNS and the size of the internet, having a response within a couple of months is actually not bad at all. So yes, it did have an effect. And interestingly, on the low size, yes, it went up. The buffer size less than the MTU went up from around 10, 11% up to over 22% of users. So, yes, it seemed to work. Let's look down at that low value, 22%. Did we do 1232? Well, that's the green line. 2%, 2%, Flag Day, whoa, 4%, 4%, 5%, yay. But what about 1400? Well, even more. Nothing, 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 nothing. Whoa, up around 7%. So 1232, yeah, some. Others, no, let's do 1400. And oddly enough, everyone's kind of pick your favorite number, because we actually observed 284 different buffer sizes sitting somewhere between a low point of 512, of course, and a high point of 1472. So, instead of having a relatively uniform thing that everyone uses, roll your own is the flavor of the month with EDNS zero buffer sizes. And kind of when we get into this roll your own environment, you kind of wonder what's going on. Are we all just rolling a dice? You know, oh, pick a number. Any number's good enough. Or is there something behind this? And if there is, what's the right number? Should we use a low value for this EDNS zero buffer size and switch early? Or should we use a high value and switch late? So let's just understand the DNS, because we're trying to carve our way through and satisfy almost two parameters at once. Everyone is intolerant of delay. And so the DNS on a good day, in fact, the DNS should ask a simple query and get an answer. One UDP round trip. No handshake, no nothing. The DNS needs to be fast. That's what we expect of it. Because that's speed is that first goal. But the problem is that when that doesn't work, you have to then pick it up and fix it up. How do you know when you haven't got an answer in the DNS? Timeout. So all of a sudden, when it doesn't work, time stretches out up into seconds. And as we've already found out time and time again, users clock their time in milliseconds. The DNS should be completely invisible. We shouldn't see it work. And so when it takes 5 seconds to get an answer, we've already raised the flag saying the internet's broken. So we can't tolerate unreliability. So should we switch early? Well, there's a time penalty, because if we go to TCP too early, TCP takes time. Should we switch late? Well, if we get it wrong and switch too late, we get UDP packet loss. So we're trying to compromise between the two. What do we know about IP? Well, the first thing we know about IP is we really don't understand packet sizes. This little table's kind of interesting. In v4, if you look at the minimum assured unfragmented packet size, what can I send through the network that won't fragment? Well, in v4, it was 68 octets. Oddly enough, bigger than an ATM cell, but not by much, but bigger. But certainly a lot less than the Ethernet 1500 octet value that became a de facto standard. When we came back in v6, sort of 10, 15 years later, and thought, well, maybe that was too small, the minimum assured unfragmented size that all compliant networks have to handle is actually much larger at 1280 octets. So in some ways, a big improvement. What should hosts accept, fragmented or not? If I send you a packet, I don't care what gets mangled inside the network, what are you assured to actually pick up? Well, in v4, 576. If I send you 577, you might not necessarily pick it up in the host. You're allowed to drop it. Bizarre. With v6, that number isn't 1280. That number is actually 1500. That's the packet that is meant to be able to make it in the host, almost irrespective of the network. What's the maximum packet size? v4, 65,000. God, I'm getting sleepy. That's 2 to the 16th, whatever that is. In v6, it's 2 to the 16th unless. And the unless is unless you go crazy, because, you know, jumbogram crazy. And yes, that's an awfully big number. It's 2 to the 32. So, okay, why choose 1232? Why settle on a v6 value? And why trigger TCP so early? How bad is UDP fragmentation loss? I'm like, are we actually triggering too early? And quite frankly, is TCP really reliable? I'm like, yes, the world runs on TCP, but that's TCP over port 443. What about TCP over port 53? Still reliable? Let's look. Before we look at some data, there are some measurement challenges. The way we do large-scale measurement is not by a small collection of active probes. That has its own strengths, and certainly they're very good, but we actually use advertisements. We do about 12 million a day across the entire internet, and we embed the measurement code inside the ad, so we get an enormous amount of data across the entire internet. How do you tell if the DNS gives you an answer? Well, you're the host. You're just running an ad script. Very hard to instrument. So we use the DNS to instrument itself. We actually use glueless delegation. So we force a resolver to explicitly resolve the name of a name server and then see if it resumes its primary resolution task. This way, the DNS itself tells us, the authoritative server, whether or not the resolution happened. And how do we experiment with DNS behavior? We pad. We pad at the front, so you can't use a truncated fragment to get the answer. And the response size we use is actually selected at random from 11 pad sizes. And we also use a control, unpadded, just to make sure you got something. The other limitation, because there was a previous talk by William Torrup a couple of OARCs ago that looked at a bigger picture, we're looking at explicitly a small picture in the middle of the network, from recursive to authoritative. It doesn't measure the edge. So in some cases, measuring the edge gives you a somewhat different picture of the DNS. So that's the first thing, we're measuring the middle. And secondly, we're resolving name server names, not target names. And for some DNS recursive resolvers, the EDNS zero buffer size is actually dropped when you're actually resolving the name of a name server. And that happens an awful lot of the time. So either the EDNS zero buffer size comes down or it actually disappears out of the query at all, which gives you a default of 512. 30% of the cases, what we measured was 4096 becomes nothing, becomes 512. So that's certainly a factor in our measurement. So the base test, we did this 4 million times for each of these numbers. And what we find is on the whole, yes.
Sorry to interrupt you. We haven't seen your slides move on since slide 11.
I'm having a fine old time. I have no idea. Can I stop sharing? I have stopped. I will move to PowerPoint. Yay. And share that. I'm not sure what the best way to share this is. Let me try the desktop. Sorry about this. My screen's gone completely dark as PowerPoint picks up. Are we on slide 12, Brett?
Yeah.
Fantastic. Yay, PowerPoint. I said all this. I said all that. I was up to here, a page of detailed numbers. I always find it really hard to talk about numbers. Two things you should know. By default, we're getting a pretty low failure rate, 0.5%, noise in the system. I can live with that. For big answers, 470 and higher, the onset of fragmentation, the failure rate inside our measurement jumps to 2.6%, which is actually reflective of the fact that in the current setup, with most resolvers giving us 4096 as a UDP buffer size, there's still a lot of failure in this system. 2.6% is not acceptable. So out of those tests, fragmented answers don't work, which is kind of the motivation behind the flag day. So this is good. Now let's have a look at those experiments that actually got a truncated answer and shifted to TCP. For low values of padding, the TCP use was around 14% or so. These are all those resolvers that when they're resolving name servers, don't give us a UDP buffer size. So we send a truncated answer, you flip to TCP. And TCP is relatively reliable. The failure rate of TCP for those low answers is around 1%. Oddly enough, for large answers, where the answer is higher than 1500, you flip to TCP, TCP is always reliable. No, it's not. And for big answers, where there is more than one TCP segment to give you the answer, the failure rate doubles. So it's around 1.9%. So what does it fail?
Sorry, Geoff. Want to tell you that you have 5 minutes remaining until Q&A.
No problem. So a truncated response with no follow-up TCP happens a lot of the time. And interestingly, and I really don't know why, that is a higher failure rate for a larger answer. No clear reason why. Also, you notice there's an MTU problem where I don't get an ACK when the answer is a big segment. So a quarter of the cases of failure for little TCP, half the cases of failure for large TCP segments. And lastly, there's a large failure rate where the TCP session works just fine. The data gets ACKed, the resolver doesn't move on. So large answers still fail in TCP. Interesting. So that just says all that. What if I force TCP? What if I always send back truncated? Well, now you get to see the failure rate coming from TCP itself, around 1.8% for large answers, 1.6% for smaller answers. Interestingly, V6 works better. Why is V4 still at around 2%? And I think the answer is there are a number of relatively ancient resolvers that still haven't quite figured out their security front ends, their firewalls, that yes, the DNS can use TCP. And my suspicion is that the failures in V4 are actually failures at the front end, not the back end. What about UDP? Well, let's just have a look at the subset here of UDP use. And yes, there is failure for fragmented UDP, around 3% or so of all cases. So the smaller response, some firewalls are even worse than you think. Any DNS response on UDP port 53 greater than 512 bytes, nah, not going to take it. Larger than that, well, fragmentation filtering. So let's see how bad this problem is if we force it. So we're going to be naughty again. Rather than going low, we're going to go high. I don't care what you said. I believe you said the DNS error size was 4096. I'm just going to substitute my own value because, you know, my reality is always better than yours. This is a protocol failure. I'm being naughty at this point. We're saying, you know, we're telling lies. The onset of UDP fragmentation happens and the failure rate when we do that is extraordinarily high, around 15%. Interestingly, this time, the UDP failure rate in V6 is significantly higher than the UDP failure rate in V4 when we fragment. Lower values, the failure rate in UDP is higher in V4 than V6. Odd. So part of the problem, 2 to 3% of the cases of users, not resolvers, of users. If I send a response larger than the DNS error buffer size, the resolver in question goes, nah, I don't accept that. I said no higher than whatever it was I said. You sent me a larger answer, not listening. It seems weird because you got the answer, but you know, you're just not going to accept it. And of course, a number of resolvers, in the case of users, 11% in V4 and 15% in V6, just don't like fragmentation. So we're now getting a picture of what's going on here. And the picture is firstly that we've repurposed the DNS error buffer size. It's no longer what it said it was. Help improve the scalability of DNS by avoiding early truncation, by avoiding the widespread use of TCP. That's not what we're purposing this buffer size for. Oddly enough, it's a fragmentation avoidance signal. It's basically saying, don't send large UDP packets. Normally in fragmentation, it's the sender that controls that signaling because it's the sender that receives the ICMP. It's the sender that gets the knowledge of the path MTU. The DNS has decided for reasons, God knows what reasons, but reasons, that it's the receiver that controls that signaling, even though the receiver has no a priori knowledge of the incoming path. So in some ways, some of these problems are that when we repurpose the UDP EDNS error buffer size parameter, we're actually doing it on the wrong side of the connection, which is a bit of an issue in the long term. Why persist with UDP? Because it's fast. Because when it works, it's brilliant. And even up to 1500 octets, 1280 doesn't matter. 1500's the number. As long as your total IP payload is below 1500 in the interior of the network, not the stubs, the interior, UDP works like a phantom. It's just brilliant. Once you fragment, abandon all hope. It is horrible. The flag day was right in that. Switching to TCP is slow. way slow, and it's not perfect. It still has a 1 to 2% failure rate. So in some ways, switch late. So what does that mean? Well, 1232 was actually too low. Go up, because TCP can't do dynamic path MTU. It's got no time budget to do that, and the signaling's on the wrong side. So unfragmented UDP, then use TCP, avoid fragmented UDP. So does one size fit all? Is the flag day right? Well, I don't think so. I think 1232 is too low. The early onset of TCP does have a marginal cost. Quite frankly, fragmentation occurs in different ways and occurs differently. Maybe we should look at differentiating based on the protocol, not on the path. Quite frankly, your DNS0 buffer size should be lower in V6 by that 20 octet different in the header, higher in V4, squeeze it as high as you can, but at the same time. And most importantly, drop the TCP MSS in the authoritative DNS servers, because running it at 1500, which most people do, causes a small but visible amount of path MTU issues in DNS. And resolving those takes even more time. So you will do everyone a big favor in not only dropping your eDNS0 buffer size, but at the same time using a much lower TCP MSS setting. And there you can afford to go very low, because the cost is TCP segmentation, not fragmentation. And what it means is that even at 1200, you're losing almost nothing in terms of protocol efficiency, but gaining a lot in terms of resiliency and performance. That's 20 minutes. If you want to spend a couple of hours reading through a couple of reports on all of this and more, the URL's at the bottom of the screen. Thanks a lot. Back to you, Brett.
Thank you, Geoff. If anyone has any questions at this time, please raise your hand and we'll allow you to unmute yourself, or type in the Q&A box and I'll read it out for you. I have a couple to start off with anyway. So first of all, Geoff, Giovane Moura asks, what zones are these servers authoritative for? How many queries per day or month do they receive?
These servers are authoritative for our own measurement domain, and every single user that receives one of these ads gets presented with a set of unique DNS labels to avoid any form of DNS caching. There are only a small number of authoritative servers, and for each individual experiment, there's only one. So there's only one server for the ad that you get. So all those queries come to one of my servers. Because I can't instrument the user, I instrument the server. How many queries per day? That's its own question. We send out around 12 million experiments per day. So in theory, you'd go, oh, well, I should get 12 million queries. Well, no, the DNS is chatty. 24, 30, 40 million and higher. But the DNS is a gigantic piece of random access, random memory. And every query that you ask the DNS is carefully recorded and replayed again and again and again and again. On some days, 90% of the queries received are echoes from previous experiments that happened months, years ago, because the DNS never forgets. So how many queries do we get per day? On a bad day, hundreds of millions up to billions. On a good day, just a few 100 million. Why? Well, all you query log replayers, you tell me. Thank you.
Thanks, Geoff. So moving on, we have another question from Yoshitaka Haran. Please, could you show me where did you measure the buffer size data from clients? Is it measured on APNIC in added servers? Sorry if I missed it.
No. This is the user in the stub resolver gets a DNS question. They send that to their recursive resolver. I can't measure that. Their recursive resolver or resolvers, depending on how they work through their etcresolve.conf, then sends it to the authoritative. So as I said on slide, I don't know, maybe you missed it. It was slide 4, 5, 6, or 7 or something. As I said, what we're measuring is between the recursive and the authoritative. We're not measuring We're not measuring the edge of the network. So in some ways, yes, this is a measurement of the interior, not the edge. We have no particular knowledge of the edge.
Thank you, Geoff. So now I have a question from Andrey Tsurio. I'm going to allow him to unmute himself. Off you go, Andrey.
Hi, this is Andrey, I see. So I think that there's the problem in this particular flag day is the mix between the vendor and the operator. So for vendor, we pick really conservative value, but as an operator, you could go higher, and that's actually what we recommend in the bind 9 documentation. So this is the problem, that as a vendor, we need to pick a conservative value so it works for everybody. But as an operator who operates your own network, you can go higher to the values you are proposing.
I think there was a vendor, Andrey. My recommendation here is to actually tune your query parameter based, hopefully, on the foreknowledge of the protocol you're working across, because you actually can squeeze performance even in a presetting by understanding that subtle difference between V4 and V6. And you can run it slightly larger in V4. The other thing that I think should come by default, some versions of DNS resolver code allow the server, not the querier, to set a maximum EDNS 0 size. So it's sort of, client, you've said 4096. I don't want to go that way. I'm going to cap it at whatever value you say. And that should also be part of the default setting. That you should, at the server level, inside the vendor code, also be going, I'm going to bring this down as part of the default setting. You can lift it up if you're feeling like, I love fragmentation, but you by default shouldn't be doing that. So yes, I understand the default setting, Andrey, but what I'm saying is perhaps you should think about a default setting that actually works by protocol difference. And the other thing I think would make a huge amount of difference is to play with the TCP MSS size settings on the TCP socket parameter. Because if you can bring that down, there's a 2% performance margin you can actually extract out of TCP, because large segments are not that reliable in today's internet.
Okay, thanks very much, Geoff. So that's the end of the questions. Thanks, everyone. So we'll now move on to our next presentation. This is around does the DGA work, and will be delivered by Eric Ziegast from Farsight. Over to you, Eric.
Thank you. All right, you see my first slide there, title slide? Hear me good?
Yeah, all good. We can hear you and see your slide fine. Thanks, Eric.
Great. Hi, I'm Eric Ziegast. I'm with Farsight Security, been one of the first engineers, mostly doing passive DNS work and managing, currently managing things that that are maybe not, the other stuff, like the things that might not get the things that might get dropped if we didn't do it. And the configure sinkhole is one of those. There's a big worm back in, that started back in 2009. There are many bots that were captured through a mechanism. There are many mechanisms for it to spread. But one of the most interesting parts is that it used a domain generation algorithm that was keyed off of what day it was to reach back home. Now, originally the bot was going back to a single server, trafficconverter.biz, but then researchers noticed that that this bot was phoning home to a randomly chosen domain from a bunch of different registries. So all you had to do is pick one of those domains, and you would have had the ability to take command and control of that client. We gave a talk about this several years ago, back in 2011. At that time, we were looking for help for visibility from TLD registries because we noticed that it used to go about 500 domains per day, but then it expanded to 50,000 domains per day, part of a cat and mouse game. People tried to contain the, people in the Conficker working group tried to contain the spread of the malware by front running the registration of those domains. But they changed the algorithm to require coordination among just generally all of the TLD, the CC-TLD registries in order to prevent it. And at that point, there was not much really we could do. There's a link to the old talk. This eye chart might have been familiar. There are a lot of lessons learned, both of what we could and could not do. It seems that the bot over time has mostly been through the attrition of the software running under it. That there were remediation efforts. There's a project called CyberGreen, which evaluated that some may have done better than others at remediation within their constituency. There's a book that was written by Mark Bowden about the sort of the social and coordination aspects of reacting to the virus. And the paper by Hadi Asghari, among others, actually showed that yes, there was some differences in remediation between different countries. There are links to some of these if you click on the images. We couldn't contain the virus, but we could at least have visibility. You could see that, yes, there was a bot that was going to do a DNS lookup and then phone home by talking to a web server. We've been operating that web server between Farsight and Team Cymru for the past, I think it's about 11 years now. It started at Georgia Tech, but we took it over to keep it going. We made data available to various organizations for remediation. And Dr. Chris Lee, who I've been working with in the development of this presentation, he provided domains using an algorithm that was developed in the reverse engineering of the bot back in 2009. And we assumed it was working because, well, we got hits. And sometimes, though, we saw that we had some false positives. And as time went on, for the Conficker C botnet, which had a lot less traffic than the A or B variant for the 500 domains, the C variant, we had a very small number of registries participating. Out of those 110, I think we still have 2. And so we're not getting as many hits for Conficker C, and it's really hard to estimate the size if you don't have a significant amount of the domains participating on a regular basis.
Eric,
and then
to interrupt, you have 5 minutes remaining until Q&A.
Great. So at every year, we just loaded another set of domains, kept going. But this year, it's 2021. He only made domains for 2020. I said, gosh, do we really need to be running this? And I reached out to some of the people who received the data. And sadly, the answer was yes. They still use it. It is still useful. But we have to question, what is the value of of continuing making the resources available and having people re-register domains on a daily basis every year. So we got a new list, but then we realized, and we had another way to look up how to make the domains. We found, though, that the lists that were generated between the 2 versions didn't work. There was the domains that Chris was generating on the left, and over on the right here, you see the domains that were Paul found a tool from one of the researchers at Kaspersky, and he ran it on, and he suggested running it on a FreeBSD 32-bit VM. And some of these domains were matched, but some of these domains did not. And so that started saying, oh my gosh, we've been running the wrong domains the whole time. And at the same time, we noticed that we had a lot of false positives from people saying, hey, why was my IP listed in this list of infected machines? And perhaps the recipient didn't fully understand the potential for false positives. For example, you can have the background noise of web scanners just going ahead and hitting your sinkhole just on the fact that it had an IP address and it had something available on port 80. But we were concerned that we were having more, at this point, at this late in the game, we were having more web crawling hits than we were actually having hits for config.rc domains. And so we figure, well, how are we going to figure this out? Well, we can run an infected client, but that's a little bit complicated, especially if you're going to try to do this over multiple days or get a comprehensive list of domains. You can't really do that very well. But then I realized, well, gosh, you know, if all these domains are being looked up by bots, we might be seeing them all because you only have a slim fraction of that data. But the root servers, if you're not using QName minimization, you can probably get a view of a working DGA. And so we grouped the names into 3 different groups. And for the diddle day, which was May 6, 2020 for the full day, Chris's names were, he had some names that were there were 49,999 49,999 names. Of those, between the algorithms, 30,000 of those names matched, about 20,000 names diverged, were different between the two. This is my first time actually doing work on the AN server, going through the diddle data. I actually saw how some other people were extracting some data out of it. I modeled that, found a way to parallelize some of it, went through the data and matched the domains from each set and counted how many hits I was getting from one or the other. And we actually saw that that Chris's list actually got 1,026 queries that were unique to his algorithm, and the domains that were unique to the other algorithm were, you know, maybe the domains are registered, or they, you know, they're actually registered and not non-existent. But it was basically a random, you know, a base random list of domains, and they did not get queries. And between the ones that were common to both, well, proportionally, they got the expected number of queries for a working DGA. Then I realized that just the fact that you register a domain might actually trigger web crawlers to go out and get you. So I excluded the TLDs from the ones that weren't from the ones that were registered, and I still had a relatively you know, good show between one versus the other. Just recently, I'm going back to 2019, see if it works the same way. And, you know, for what I have so far, even today, it's actually showing that, yes, the algorithm and the method that Chris is using is actually proven to be working. So after the initial results that I found, without doing a full summary, it gave me the confidence to go out to the TLD operators and ask them to register some domains. And so this isn't really you know, earth-shattering DNS research. It's more of a thank you to people who for making the data available. Because of it, we actually could figure out that, yes, the DGA algorithm we're using to get domains to point to the sinkhole actually was working, and confirm it just through looking through data. We theorized what was wrong was actually that the DGA algorithm uses a combination of floating point and integers, and that there's a math library in Windows that provides a different result for a logarithmic function in the very least significant bits all, out in the point of noise where it all gets rounded out. There was actually a difference between two algorithms, and that was leading, as you call the function again and again and again, that you would actually end up, as the bits are copied from floating point to integer, it would actually make a difference in the name that's created. And so that's why 40% of those names seem to diverge between the two. And so there are a couple papers here. You can go ahead and click on them. The specific note about this divergence is in the second paper on page 13. Know your KYE. Any case, we realized that there's a little bit more we could do to help avoid some of the false positives for getting config.c data out. The amount of usage we're getting config.c is so low that it may not really be worth the effort. There are so many other bots out there that have so many more clients in them. And in fact, AB still have a significant amount of phone homes that it's still worth us to monitor that for infections. But the C effort is probably about time for it to wind down. And maybe it's overdue, but no one told us, yeah, you should do this, you should wind it down. But now we're looking and saying, yeah, let's see what we can do to do one little last push and then be done. So thanks to Chris Lee, the registry operators that participate. And if you want to shout out, go ahead and say that, yes, we're participating over in the chat. I don't assume that you want acknowledgement. The ISPs for the address and connectivity, CWG members, and also for Team Cymru for continuing to run the sinkhole that helps provide data. And, Farsight, my day job, which actually, through paying my day salary in part, it helps make this effort, continue to be operated. And also to DNS-over-QUIC and root operators. This may have been one way you didn't expect the data to be useful, but it is useful. So thanks for making that data available, and for the monks that make it in a usable format for us to use.
So thank you, Eric. If anybody, we're running over time, if anybody's got a quick question that they want to ask at this time, raise your hand or type something in the QA quickly, and we'll ask that. Also, please fill out the poll that is about to pop up, and will be available a couple of minutes into the break. I am not seeing any questions, so in the interests of timing, I would say we go to the tea break now. We will be starting back on the dot at 17:10 UTC, so just time to get yourselves a quick cup of coffee or tea, and we'll see you back at 5:10. Thank you very much, everybody. Welcome back, everyone. I hope you had time to refresh your tea and coffee cups and you are suitably rested after a few minutes. Next on the agenda, we have a presentation from Giovane Moura titled Old But Gold, Prospecting TCP to Engineer Real-Time Monitoring of DNS Anycast. Over to you, Giovane.
All right, you folks hear me?
Yep, we can hear you.
All right, and probably can see my slides as well.
We can see your slides, no problem, go ahead.
All right, so good evening, everybody. My name is Giovane. I am with SIDN Labs, and this is a work I've done together with some colleagues at USC, ISI, John and Wes, Jeroen at Operations Department of SIDN, and Jeroen and Christian at SIDN Labs. As you know, I mean, if you run any authoritative server or service, you know that latency is key in DNS, but it's sort of a hard measure because, well, most of the traffic is UDP on DNS still. So as an operator, you would do whatever you can to reduce latency. You would use multiple NS records, you deploy Anycast, you're gonna peer, or using internet exchange points. You do whatever you can to reduce latency to your clients.
Giovanni, we're getting a little bit of static. I don't know if you're hitting your mic with something.
Oh, okay. Let me see.
It sounds like you're just brushing against the mic or something like that.
Oh yeah, I hear what you say. So I'll hold my mic like this, probably be better off.
Thanks.
Let me know. Yeah, so it's kind of it's hard to know client's latency because most of the traffic is UDP. And what folks actually have is Bright Atlas. That's one of the things you can do, or a commercial service like Thousand Eyes. They're very good, but like they have not complete coverage and they not necessarily overlap with your own clients. On the other hand, what you can do is also use a technique called Flurflutter, which is an active measurement technique that you would ping the entire V4 space. Portions are based on a hit list, and you would do the pings, and you're going to collect that on your Anycast network, and you can actually measure the latency from that to your sites. The thing is, you have to typically it's run once a day, and it's expensive to run in terms of CPU resources and network traffic, and it's hard to apply to V6 because of V6 hit lists are problematic. So we wonder if there was a better way to do that that would allow you to get measurements from real clients that works well with V6. It also requires no extra measurements, being namely passive measurement. And you can actually do that with TCP. You can measure the RTT from the resolvers that are your clients to your authoritative by measuring that on the handshake session or during the takedown of the TCP connection. And we've been using that for over 1.5 years at the SIDN, and that helped to solve several issues, and that fulfills all the above requirements. So TCP RTT, it's an old technique to measure latency or RTT on TCP. It's a very old technique. It's been first deployed in 1996. I think that's the year I actually got my first computer as a teenage boy. It has been widely used by, for example, HTTP for HTTP. There was a paper on IMC 2 years ago to just describe how they do that. And it's been applied to DNS multiple times. Roy Arends came up with this idea in 2012. Casey Ditchu in 2018, that's the one that triggered his work. Machi as well, and at the Czech folks, they did the TLD did that in 2019. And we have this technical report for 2020. So it's like it's an idea that started in 96, but the novelty here of our work is to apply that to actually investigate that extensively for DNS and apply that in this context. So what's new is that we have an extensively comprehensive methodology validation. So if you get TCP data, doesn't mean that is that data representative from your overall traffic. I mean, you're getting biased view only for TCP clients. I mean, and you also have to answer the question if you like, you get TCP measurements, are they representative as well for your UDP clients? In other words, can you really trust them? And also what we did in this work is not only measure that was the easy part. The hard part is to analyze this data in a way that you can actually make engineering decisions in operations and So what it did, we applied those measurements and identify problems in several use cases for this data and solve issues in for an Anycast networks. And we team up with Google to solve one of those as well. So we manipulated BGP to fix all those issues, and you document that carefully. And it has been used in .NL in real time to detect anomalies, for example, like route leaks. So to actually trust it, this the measurement of DNS, TCP, RTT, TCP traffic must provide enough coverage, both spatial and temporal, because most traffic is to use UDP, and you have to have similar latency for UDP to UDP, so you can't generalize the results. So this is a table of traffic we analyze. We collect this week of traffic 2019 from 2 Anycast networks servers that are for .NL. They're run by different providers. And what you find here is in this green color line here is that the TCP traffic informs only 2 to up to 5% of all the clients, of all the queries, they're actually TCP, but 20% of the resolvers, they eventually send TCP traffic, and 43% of the ASs send TCP queries, and you have similar figures for V6 here, this line in the bottom here. So it means like you get 5% of the queries, 20% of the resolvers, 44% of the ASs, and you get this for free. And it depends on the network because the roots DNS, they have a different proportion of TCP queries, 1.7 to 14. But what do we know from DNS traffic as a TOD, in this case, .NL, the Netherlands is a TOD, if you get all the traffic that you have, but then you're gonna say, well, how much traffic does those people that actually, those resolvers, that those autonomous systems that send TCP traffic? Well, you get like 98% of all the traffic. So all the ASs, they matter, they eventually would send TCP. So these people that are not sending TCP, probably they're not the ones that your most query ASs. So they give us confidence that you can trust this because they're focusing the ASs that send most traffic. They eventually do TCP. You can see here 98% for V4, 98% for V6. So that was the first thing. You can actually, that proves that you can actually use that. We also have temporal analysis on the paper, but I'm going to skip that. You can relate the report. And also did a measurement with RAP Atlas for to two other Anycast networks, K-root and L-root, and a query using UDP and TCP, and we had like this number of probes querying directly those root letters, and we roughly had 3 million queries for UDP, 1 million for TCP for each of them, and then you compute a latency from based measured on UDP on the client side and on TCP on the client side. And you see they're roughly the same. The CDF curves, they're so close together, both the median and the 90th percentile, that shows that you can actually trust that. So that means that if you get a TCP measurement from a certain network, you can expect that from a certain IP, you can expect the same latency for a UDP client. So that was the fundamental work, like the foundation work. And the question is, what you can do with this data? And that's the thing we got us interested. So let's show a couple of examples here. So one of the things we did, we kind of aggregate all the data, and for example here, for Anycast B, that's one of the servers that we have for .NL, and we got aggregated metrics for each site, and these green lines here show the spread of the RTT. The median is the median. This, for example, this site here, let me get this one here is LAX, has like roughly 100 something RTT milliseconds here, and the spread goes from above 150, and the 25, the first quartile below 50. So you see which sites have a longer spread than the others, and with that you can identify problems and try to solve issues. You can also do it by the same analysis, but instead of aggregating per site, you can do per autonomous systems that they want to send you more queries. So for Anycast B, for example, you see that 15169, that's Google, send most queries. I think that was 1 week, more than 400 million. And they have a sort of a stable RTT over here. But you see that 13335, they have a much more distributed spread RTT. So those are the things you can actually look upon and see what's the problem. And this one here, 4134, sent, okay, not so many queries, but like maybe 30 million or so, but the RTT is pretty high. So this is how you get with TCP, the TCP measurements. And one of the problems we solve is what we call distant lands. So BGP, you have no control the way they map clients. They map IP addresses to the different Anycast sites. So we found, for example, some sites were having very large RTT or value or spread, like Charles de Gaulle in France, Singapore, or Tokyo, Narita. Here, Tokyo, for example, Narita, you see that the spread is from a little bit under 90 milliseconds to up 140. This is all measure of your passive TCP data. And we went to figure that out, why was that. So we singled out all the queries that came to Japan side, and turned out that most of them came from China. In China, this particular provider has no presence in China, and China is well known to have international connections that have congestion. So you see that, for example, this is a particular autonomous system here sent like 3,000 queries on this particular week for us for this particular server, and had a median RTT of 130. And you see that goes for the others as well. So with that, you can say, well, okay, that's a problem. How can you fix that? You can run a site in China, but I talked to the operator and he was like, oh, maybe many of my clients would not be comfortable. We have their own files on inside the Great Firewall of China. I understand that. Or you can also direct peer with Chinese ISPs, which I've been reported is very expensive as well. And only very recently they have allowed to do that. Direct peering inside China. So that's one of the things we can do. Another thing another problem we found is it's a common BGP policy, which means preferred customer. So there's a route that goes via an autonomous system that satisfies that particular requirement. It's a via customer, so be it. Which means that given that BGP is not our latency, it's totally latency agnostic. Actually, we found that Comcast or V6 was sending all the traffic that were actually being mapped by BGP from Anycast B. They're going to the site in Brazil. And you see here all this latency, the spread of the latency. It goes from less than 40 up to 150. So we talked to the operator and they figured out there was an issue in the BGP community. And then just by changing that, and this is the data we get from TCP data, we saw that once they fixed the community, all the traffic from Comcast in the US remained in the US. It was mapped from the Brazilian side to multiple sites across the West. That's a process that the Anycast B has. And you can clearly see that on our measurements right away. So the RTT was significantly reduced. So again, this is only using passive data. This is real clients data. And that's the power of this technique. And another problem we found, it's what we define as Anycast polarization. It's when a large autonomous system just sends traffic to only one of your sites. So if you have an Anycast system with multiple sites distributed across the globe, and you have like a large autonomous systems like, that's for example here, Microsoft sending you more than 400 million queries to this particular server a day, and Google more or less the same here. But then you see the Microsoft has a sort of a latency which is not so good. It's like 75 milliseconds, and Google has a massive spread here. So you see, they're just like, they're big clients, but they're not getting good latency, for example, as those here, as this one in particular. So we found later on that, let me get the example of Google, all traffic from Google was going to one site only in Amsterdam. And then you see here, this is the line of days for January 2020. And each line here is a different Anycast site that this Anycast service has. And you see all the queries from before for this particular day for these days were only hitting Amsterdam. So we did a bunch of BGP manipulations. We withdraw the routes and then we start tuning that. And that in the end, I wanted folks to focus on the red line. That's the RTT, that's latest, that's what really matters. The median RTT for all the clients from Google was dropped from 100 milliseconds, and after our withdrawing and route manipulations to 10 milliseconds. So because of the insights we got from TCP, you can actually act upon the data and improve our networks. And that's what it did. And see, that's the current status right now. The median RTT is 10 milliseconds for Google, which is great. We also found the same problem with Microsoft, but the thing is, they were not sending only to Amsterdam. They were sending, we found this Anycast provider, was a different one, no, actually it's the same one, was having direct peering only with Microsoft in one location, and that caused polarization because there was like, the BGP distance was very short. It was only one hop distant. So we talked to them and they depeered that site and immediately, so the latest before was around 100 milliseconds. And after that, you see a reduction significantly as well. So we were able to fix this polarization with BGP.
So to interrupt Giovane, you have 5 minutes remaining until Q&A.
Perfect, thanks, Willem. So these are the things we fixed, but we also wanted something more reactive, something more dynamic that can help us not only post-mortem analysis. So what we did to create a system called Anteater, which pretty much this is for example, this is one Anycast network, and these are 5 sites. We have a tool called Intrada that actually ingests all this data and puts in a nice format for us. So Anteater is just a tool, a set of Python scripts that reads this data from Intrada, the RTT measurements, and put in a database, and then you connect to Grafana and you get a nice graphs. And that's what you have right now, real-time monitoring that I know of this. I mean, I would say near real-time monitoring because there's some delay between exporting the traffic to Intrada and then getting Anteater to query that. But still, so this is an Anteater. It's a nice animal. This is my dad took this picture this week while he was mountain biking. So that was a random name for the system. And we use that to detect route leaks. So this is another example of what happened to a particular site of this Anycast network. This site had an RTT of roughly 20 to 30 milliseconds average, and in one day it went very high. So we get alerts by mail, say, hey, particular site, Sydney, it's getting like a large RTT. There's a massive increase. You better check it out. And when we went to investigate what happened, you see the number of queries going really high, and also the resolvers. So we talked to the operator, and the operator said, well, we have a tier 1 ISP there in this particular site, and they propagated our route beyond what they should have done, and that brought all the traffic from Europe. So you saw all the EU traffic, instead of staying in Europe, it went to Australia, and that caused this massive delay. So they already, I didn't have to notify that. They already were, did notify them, but they were on it already. And they withdraw the site for a while, and then they put back again, and you saw the latest is being reduced again. So, but we are there now. We are hired the service from another provider. We wouldn't have known. That would be very hard to know that had actually happened if we wouldn't be by the system. So in summary, this RTT measurements from DNS are very useful for Anycast engineering. We show how we prioritize analysis per site, per client autonomous systems. We use that in 3 different Anycast services, A, B, and B root. We document polarization. We shadow latency in various cases in up to 90 milliseconds. And Entrada, if you want to Entrada, you already get those measurements for free, meaning like it computes already the RTT for you for TCP. And we've been using that for 1.5 years in SIDN. If you're interested to read more, this is the link to the technical report, which we should be updating soon. And with that, I open to questions, I guess.
Thanks, Giovane. It's 2 minutes ahead of schedule, so that's good. If anyone has any questions at this time, please raise your hand and I will allow you to unmute yourself or type in the QA box, and I'll be happy to read out your question for you. As in previous talks, a poll should be appearing on your screen at any second, and we would appreciate your feedback on the talk. So I see 1 raised hand, 2 raised hands so far. So I'm gonna allow Makie. Sorry if I've mispronounced your name. I do apologize. You should be able to unmute yourself and ask your question.
So thanks for an interesting presentation. As you already know, in CZNIC, we did exactly the same analysis 2 years ago. And I first presented it in May 2019 during the Jamboree in Amsterdam. So basically, our conclusions were quite similar. We found this method to be very powerful, and it helped us to identify locations with poor RTT. And we did some BGP tuning, and we deployed servers in new locations, like in Singapore. So all these changes helped us to reduce the RTT in some locations. So if you are interested in our work or in this topic, you can find out more on CZNIC blog.
Okay.
Yeah, so just the comment. So that's it. Thank you.
Thank you very much. Next we have a question from Benno Overrinder, which I'll allow you to unmute yourself, Benno.
Hi, Giovane. Thank you for the presentation. You mentioned that you use it at SIDN, but probably so you have the monitoring, but you use well, human intelligence, I think. So you do the analysis and act. Are you thinking to create a dashboard or some more automated alerting and analysis tooling?
Yeah, we have it. We call it Anteater. Entrada just pretty much crunches the PCAPs and put it in a format that we can actually read. And Anteater gets this data from Entrada and put it in another database. And then they connect to a Grafana dashboard. And that's what we have running. And for example, I could show here, but I don't want to mess up with this in real time right now. But you would get a dashboard. We have a dashboard running in real time now that you would set an alert, say, hey, if Google is getting more than 100 milliseconds for this particular server, send an email. And you get all this, it's already running. It's been running for a while.
Okay, the alerting, okay, excellent,
It's here, it's Grafana,
yeah.
Because that's the important part. I mean, because otherwise, I mean, you need this in real time as well.
Yeah, no, with the alerting, I understand. Then you get informed and act. Yeah. Thanks.
Yeah, and that's how I actually found this with Sydney, the case. Was an alert that I got. See, like when this RTT from the site went up above 200, it was like, whoa, what's going on? So get an email, you go there and you check.
Thanks.
Sure.
Thank you, Benno. Just a reminder to any people asking questions to mention their affiliation. So next we've got a question from Roy Aaron. So I'm going to allow Roy, you can unmute yourself.
Thank you for the presentation, Giovane. I've got a question about, my name is Roy Adams, I work at ICANN. Have you considered correlating hop count with RTT as well? I'd be interested in seeing those results if you have any. Thanks.
I think you did some work on that. I saw some of the presentations before. I never really look into that. That would be very interesting to see that, especially in the case of polarization. But no, short answer, no, I cannot. No, I haven't never done that. But it would be interesting though.
All right, thank you.
Thanks, Roy. Next, I have a question in the Q&A panel from Martin Bostils. Giovane is asking if Anteater is open source, and Martin's from DNS Belgium.
What is open source? Sorry?
Anteater.
No, I mean, no, it's not really open source now. Probably can do that, but Anteater is really specific to Entrada. So it's just a bunch of DNS SQL queries, and they store in a database. I mean, the hard lift, heavy lifting is done here. And here, just say, well, give me the RTT for the last 10 minutes for this autonomous system over V4 or V6, and it's stored in another database. And Grafana reads that information. But I potentially could open source. We never did it, but it could. But you would have to have Entrada for that.
Okay, thank you. So thanks everyone for the questions, and thanks Giovane for the presentation. We will move on to our last presentation before our 1 hour lunch/dinner break. This is a presentation from Patrick Cullen on making DNS just work at scale. Over to you, Patrick.
Hey, thanks very much. Let me just share my screen, guys.
Yeah, we can hear you and see your presentation. Thanks.
Great. Okay, well, again, thanks for the introduction. This is my first virtual conference, so hats off to the team, by the way. Great work, making it all look easy. That said, I miss jumping on a plane, so hopefully we're not in this mode for too much longer. Okay, so my name is Patrick Cullen. I work at Facebook. I'm part of a team that endeavors to make sure DNS works reliably at Facebook. And on the face of it, that's not such a tall order, right? Because DNS has been around, as we all know, for some time. It's well into its mid-30s now. So making it just work shouldn't involve too much poking and prodding. So as it turns out, as we found out, it's never that simple. I think as we all have learned in the last 12 months or so, we don't live in a static universe, and we've all been seeing a lot of growth in demand. And at Facebook, we've got growth and we've also got scale. So that's kept things pretty interesting. And, you know, before I go deeper into the talk, you know, just up front, this isn't a talk with any overarching theme or big picture idea. There's no grand vision or shiny future. Instead, what I'm going to talk about is the problems we've tackled over the last 12 months or so, some of the challenges we faced and how we tackled them and what worked for us. And every time we leveled up, what the next boss battle looked like. So it was really a case of one step at a time. So I'm going to talk a little at the beginning, give a quick backdrop on our scale, and talk about how we do naming services at Facebook before I dive in a little more into some of the challenges we faced. Things like hitting the limits of CDB, the benefits of divvying up our DNS workload, reducing the burden of unnecessary DNS queries so that we can be a better peer to others, and the challenges we faced in speeding up how quickly we update our DNS records. So let me draw a quick picture. So we group DNS at Facebook into three main groupings, let's say. We've Corp DNS, which caters to Facebook employees. And then we've Edge DNS, which, as the name may suggest, focuses on user traffic. So it runs typically on POPs. We've got a relatively small set of records, and these are all user visible. And a good example of this would be fb.com, right? And the interesting part with Edge DNS is how we do load balancing of traffic based upon how users are coming in, which regions, and so on. But the area I'm going to focus on today is our prod DNS. This is the internal DNS we use within Facebook. So all the machines in our data centers use prod DNS. So it's got a huge set of DNS records. And this is where we spent a lot of time over the last 18 months or so reworking various components. So just going to talk quickly about scale first. We've seen a big increase in load over the last 12 months, and equally we've seen a big growth in the number of records that we're serving up. So we've many records, and this growth is kind of continuing each year. I want to talk a little about the resolver. This is the most critical part of our infrastructure. And any issue with our resolver layer causes a major headache. So this is a simplified DNS resolver. We have an authoritative DNS server. It's responsible for the zones we manage, and zones, facebook.com, fb.com, etc. However, this isn't enough. We need to get internet records as well, such as google.com, etc. So for this purpose, we have a recursive DNS server up front, which talks to both our own authoritative DNS servers and also to internet resolvers. And the recursive server plays the role of a kind of a balancer of queries. It either directs queries to our own set of servers, our own authoritative DNS servers, or in other cases, it'll direct the queries outside to the public net. And because of that, we need a public IP address to reach internet services. Now we use Unbound. It's an open source recursive and caching DNS server, and it can handle a huge volume of queries a second. and it's pretty feature rich. It's got some key features which we like, such as DNS maps, so we can return different answers based on client location within Facebook. And for the authoritative DNS server, we were using TinyDNS, very fast, very simple. One of the disadvantages we had faced with it was that it didn't support very new, very recent features. So it's very secure, but perhaps not as flexible. But this was our effectively our status quo for some time. So let's take a look at the authoritative DNS server itself. So for starters, what we did, as you know, one of the early things we did is we separated our DNS records into two groupings. We have a zone which contains public records, that's our external shard, and then we had one focused on all our internal records. So we would run two instances of TinyDNS on the box, and then use Unbound to direct the queries. And one of the reasons we did this is so that the external zone, the external scope data set, let's say, it could be used on edge resolvers as well without any changes. So this worked, as I said, but not having some of the newer features became a challenge, specifically eDNS, supporting newer generations of maps, ECSI, and so on. So, at one point we decided we were going to do a drop-in replacement, and we swapped out TinyDNS for FBDNS. This was developed inside Facebook. It's similar in terms of its function, and it's written in Go, but that's probably one of the major differences. And we can obviously add features as we see requirements. So this was great. We now had more control over which features we could add to our authoritative DNS servers, but we were still hitting another bottleneck, and the bottleneck was CDB, because both TinyDNS and FBDNS use CDB as a storage backend. So CDB offers a lot of advantages. It's super fast, but there is one major limitation, and that is it's got a maximum size of 4 gigabytes. And so this became a squeeze. We were getting closer and closer to that line. And if we hit 4 gigabytes, CDB wasn't going to compile. So one of the things we started working on early on was breaking up CDB. So effectively sharding our records. So we split our internal shard into multiple shards. And with some tinkering, we got load balancing to work so that we were load balancing kind of fairly evenly among the shards. But even with that, we started approaching the 4 gigabyte limit with the individual shards. So we had to take another approach. And the answer to that, in our case, was RocksDB. So CDB, it's a key value store, and there's plenty of products out there that provide that type of functionality. So we had looked at a bunch of alternatives, LMDB, Badger, and so on. But RocksDB, for our use case, offered very good performance, very good lookup times, and in certain use cases, like with keys that are lexically close, we saw very good performance. So this was great, especially for ECS maps. And the other big advantage is, CDB is a constant database. Every time you change anything, if you change a single record, you have to recompile the entire database. And so that takes a while. It takes generally, in our case, it could take over a minute, and it was burning CPU. With RocksDB, that wasn't a requirement, and it meant we could actually update the database far faster. In fact, we were able to cut the updating time down dramatically. And as a result, we saw faster record propagation. So we were able to reduce dramatically how quickly records propagated to our DNS servers. So this means clients can, more quickly resolve new records. And teams that we work with that are provisioning new compute and so on, for them, one of the bottlenecks with provisioning can be waiting for the associated resource records for those new machines to be available in DNS. So this was a big win for those teams in particular. And one other big benefit was the size of the database. So, previously we had to repeatedly recompile CDB. So this generated gigabytes of data. And at one point we moved to TempFS because we wanted to reduce the number of writes, the number of writes to SSDs and the wear and tear we were placing on them. But by going to TempFS, obviously we were consuming RAM. So we were allocating a chunk of RAM for TempFS, and it left us with less RAM to actually process queries. So being able to drop TempFS down to a much smaller size, about a third of what it was previously, meant we got better cache hit ratios, we had more RAM available to do the thing that we wanted it to do. But then we realized one of the other things we could go back to doing was stop using TempFS altogether and go back to using SSD. So that's ultimately what we did. So we'd made good inroads on the authoritative DNS side of things, right, with the changes. And so we were now in much better shape in terms of that layer. FBDNS made a big difference, RocksDB made a big difference. But recursion was the next place we started to see we needed to do a lot of work. So let's put back this picture. So we have Unbound at the front, and it's sending queries to different shards depending on the zone. So, greenfacebook.com, as an example, is going to the internal shard. Bluefacebook.com is going to shard 4. Our internet queries are getting sent out to the internet, and that's, that works. And it's all controlled by the Unbound config. So we explicitly call out, where queries need to go. And so you end up with an enormous configuration file. So many thousands of lines. It was working, but it was a fairly large configuration to generate. And some of these records, or some of these queries that we were sending out, required public IPs. So what it meant was every one of our DNS servers needed a public IP address, or multiple public IP addresses for v4 and v6. And so this was extra work for us to manage as a team looking after DNS. We were dealing with a lack of availability of v4 addresses. We were having to advertise these public addresses. And when we were provisioning and turning up new DNS servers, it was extra work for us because we were having to acquire and allocate those to our hosts. So moving compute around was more of a headache for us. And as we typically run on bare metal and we don't run within containers, as is very common at Facebook, we were in the hot seat when it came to moving services or accommodating works. So the burden of ownership was greater than we wanted. So what we decided to do was move internet recursion out from our servers, from that tier of boxes we had, and put our recursors in containers in a separate grouping. So our regular DNS servers that run on bare metal would simply send the query to these containers who focused on simply recursing internet queries. Now, because there's relatively few external domain requests, we can have a smaller number of internet-only resolvers. So it's a small set of boxes, relatively speaking. That means we've much smaller demand for public IP addresses. And it means we could now introduce internet-only DNS infrastructure. So services that just needed internet-only resolution, instead of rolling their own, they could come to us. And one example is, proxy servers that proxy HTTP traffic out to the internet for our machines in our data centers. One other big win here, and I don't have a before picture, but our after picture looks great. We were getting cache hit ratios between, 80 and 95+%. So, fewer boxes meant much better cache hits. And it also improved our latency. So our latency dropped significantly, and it also freed up RAM. So we were getting a lot of wins across the board simply by divvying up the work.
Sorry to interrupt, Patrick. You have 5 minutes remaining until Q&A.
Great, thanks. So here's the thing though, we still have a lot of queries going out. So, and most of these queries are answered by caches, but even with the caching, we still have a lot of queries that go out to TLDs. And this can cause outages from time to time when TLDs ban us. And this is generally our fault. And the reason is, here's a typical DNS request. Because there's no dot at the end of this query that the host command is running, every single search domain is appended. So we end up with multiple requests, all of which are returning NX domains. And then when nothing is found, a dot is appended and the FQDN resolves. However, in this case, as it's an invalid, we're gonna end up getting another failed request because there's no top level domain foo. So these types of queries are a constant headache for us. So the solution was pretty obvious. Stop sending invalid queries to top level, to TLDs. And so we implemented two things. First, what we decided to do was fetch all the TLDs from a centralized repo. There's about 1,500 at the moment. And when we generate the onbound config now, we simply say that queries for TLDs should be forwarded to the internet-only resolver. So, for example, blue.facebook.com will go to shard4, but everything ending in .com will go to the internet-only recursor. And anything that's not specifically called out, anything not in the config is immediately refused. So what we call this is turnip. And the advantage of this is before we were seeing very few refuses, now we're seeing a lot of them. And the reason we are is we're responding directly to clients. And these are queries that otherwise would have gone to the root servers. One other great win here too is we got a big speed improvement. So previously we were going through internet recursion and the answer was being returned. I mean, it took many milliseconds to get an answer back. So now by refusing the queries immediately, we're saving on compute resources. And one other thing we're going to do to build on this now is instead of simply returning refuses, we'll start returning NX domains. So the difference there is we're telling the client the domain does not actually exist. And that prevents the client from, re-requesting, because sending a refuse back may indicate to the client that the request is coming back refused because of policy on the DNS server, as per the RFC. So by sending NX domain, we prevent those retries, and that reduces the number of queries we're sending out to our own infrastructure. And then taking another step down this path and using the same turnip data that we referred to, we now have the internet recursors act as root servers themselves. So we're not even recursing to root servers anymore. So we're operating as a root with a flavor of turnip. And courtesy of VeriSign, we see an impact on DNS servers here, whereas before we were sending millions of invalid queries, we now send 0. And even for valid queries, we're answering or responding to valid queries as well. And last but not least, let's talk quickly about propagation. So I want to stick up a lot of boxes and rectangles in this slide, but what we're going to show here is a typical pub sub architecture. We have the resolver we talked about earlier. The records themselves that go into DNS are gathered from a lot of different resources. We use thrift, which is what Facebook uses for inter-service communication, to get this data into DNS mutator and from there into a key value store. Then we have a presenter component, so we can suck in data from human generated configs. And then we send it to publisher, and publisher generates the full view, which is what we send via BitTorrent to a component called subscriber running atop all our DNS hosts. So the design's pretty simple, even with all the boxes. It's standard pub sub, but the main challenge we faced here is the time it takes to get from the beginning of the pipeline to the end. And so at the beginning, when we were looking at this, it could take 45 minutes to get from the data sources to production DNS. So we focused on some of the components and we ported them to Go. So these were drop-in replacements for a DNS mutator, the presenter, and the publisher. This got us down to 15 minutes. This was a big win because these were drop-in replacements. And then we brought RocksDB into play. We were able to change our pipeline to propagate only the changes and not the entire database. So that, along with rewriting the components, got us down to about 2 minutes. And what we're working on now is torrent propagation. So torrents historically require, and generally do require, trackers. And this was often a cause of issues for us. Propagation would stall because of the trackers being unavailable. And so one of the things we brought in this year was trackerless torrents. So using PECs, torrent nodes can actually share information without having trackers be present. And so this is simplified. It hasn't necessarily made the pipeline faster, but what it has done is made it more robust. And just some final takeaways before I go. So again, as I talked about at the beginning, despite the fact that DNS is used everywhere and problems are supposed to be effectively solved already, it's still developing. And there's a lot of new things still coming. DNS over HTTP, DNS over TLS, and so on. And the other conundrum here is uptime expectations of DNS are high. People expect it to work because it's a utility service. So we need to be able to add these new features without bringing DNS down, effectively change the tires without pulling the car over. And when we mix in growth and scale, it makes it harder again. So what we found, what works for us, is taking an incremental approach. Small wins, building on those wins, not expecting there's a silver bullet solution. And finally, in a plug for Go, Go loves DNS. Thanks, Phil.
Thank you, Patrick. Very interesting talk. So we're running a little bit over time, and I've got 3 questions in the queue. So I'm going to close the queue for questions already, I'm afraid. Please take a note of the poll that's about to appear though, and answer the questions. If anybody has any other questions for Patrick, they can ask them in Mattermost or the social afterwards. But I'll plow through these questions, see how many we get through. So Paul Ebersman asks, do Facebook client apps on user devices send their DNS lookups to the device stub resolver or to your unbound recursive resolver?
So all queries go to the unbound recursive resolver. So we advertise our unbound resolvers, IPv6, Anycast typically. So all queries will go to that tier.
Thank you. Paul McCheney asks, do Facebook also employ NSEC caching to minimize responses to NX domain queries?
Well, it's something we're looking at, but it's currently it's effectively a work in progress, I would say.
Okay, thank you. And last in the question queue is one from Sven van Dijk. Are you also planning to enable DNSSEC for the Facebook domains, and how will that fit in the pipeline?
I mean, that's definitely in the works. But just before I continue, I wanted to go back to the first question, because I guess working at Facebook, we're looking at different groups of users effectively. Facebook users of the app who are coming in from the public net, they're not going to hit an instance of Unbound. So what I was focusing on the talk here was production DNS, which is focused on machines within data centers. So if you're coming in as a user of Facebook on a mobile device, you're not hitting Unbound. You're hitting our edge DNS infrastructure, which is it's a different it's a different block of compute entirely. It's, you know, there's some similarities with production DNS, but it's different. So you're hitting a load balancing service up front to direct you to the you know, the appropriate nearest POP for your device. So sorry, getting back into the last question. So again, it's in the works. Nothing to share publicly at this time, but obviously we're trying to stay close to developments, and it's definitely something we support.
Okay, thank you very much, Patrick. Thanks to all our presenters from the first session this morning, or where you are. Some great talks there and good thought-provoking questions. It's now time to take our hour-long break, but before that, a few words from Keith.
Okay, sure. Thank you, Brett. Yeah, Patrick, if you could just stop sharing your screen, please. So yes, thank you to all our speakers for this first session. That all went very smoothly. Thank you all for being on time. And a special thanks to Brett for chairing it. That's the first time that we've done audio and chat questions at the same time. So there's a bit of multiplexing to be done there, but I think that all went very smoothly. So thank you all for the everyone who's asking questions, for engaging and playing ball. I'd just like to remind you of a few things before we break for meal break, depending on what time zone you're in. First of all, I would like to thank Farsight as our sponsor for this workshop. It's always great to have a sponsor. Farsight are an OARC supporter in many various ways. So we appreciate them being sponsors. If you're interested, we're looking for sponsors for OARC 35. So we'd please talk to Dinesh if you'd like to do that. For the 1 hour break today and tomorrow, and for the social afterwards, we're running a Zoom room. You can see the that bit.ly link that Dinesh will make available. Meeting ID is on the slide. The password is 846907. So we'll be starting that up shortly. We will also be continuing the webinar room through the break. There just won't be anything on it if you want to hang around while you go off and refresh yourselves. All OARC members and supporters should by now have received their invite for the closed session tomorrow. If you have not, please email admin@dnsoarc.net before it, well, as soon as possible, preferably, and certainly in no event later than 8 AM tomorrow morning. Basically, we're now going to break for an hour and restart at 1900 UTC. So thank you, everyone.
Hello, everybody. Welcome to the third session of OARC 34. I'm Pallavi Aras, member of OARC Program Committee. I'll be the session chair and Jan will be the timekeeper for this session. In this session, we will hear two presentations followed by a 15-minute coffee break leading to the final presentation of the day. Now I would like to welcome Jason Weil and Todd Medbury to talk about the lessons learned during Charter Communications public DOE trial. Please go ahead, Todd.
Good afternoon, everyone, or good evening, or good morning, depending on where you are. My name is Todd Medbury. I am a principal engineer with Charter Communications. And this is a readout on our deployment and testing of our DNS over HTTPS platform. The initial testing of the DOH platform and load balancing setup was performed in our data center architecture lab. The initial setup allowed us to test end-to-end, making sure I'm on the right slide, the entire DOH stack. The testing consisted of one DOH server in the middle and two separate load balancer setups from two different vendors with two separate backend setups in parallel. While this type of testing is not that incredibly interesting, it did bring to light a few interesting items. The first of which was that load balancing setups are not used to health checking non-standard HTTP requests or HTTPS requests. And the initial health checks for the end-to-end testing were performed as simple L4 port checks. During this testing, command line clients were used to create requests, not for load, but to help understand what response codes would be encountered and what they meant when one protocol was used to transport another. This ended up turning out to be less of a concern than we initially thought, as the 200 OK sequence was generally available for any server response, and 404s were seen predominantly by misconfigured clients. In this section of the testing, the most interesting piece discovered was that one, it works as advertised. This is new technology for us. This is fairly new to the world of DNS. So for, to have a success out of the gate was very welcome. Number two, the fields are base 64 encoded, making the crafting of health checks that go beyond a simple L4 test more difficult, and we'll be talking about that a little later. Once the platform moved from to the larger production instances and before we were sending the stack live traffic, we wanted to ramp some traffic towards the platform that would mimic live traffic from our customers. So there was a few ways this was done. An external company was used for both testing and to supply DOH load and provide statistics and graphs. This provided some really good information, but really wasn't stressing the environment as much or in the ways that we had wanted. So what I did was I took the logs from my family's DNS server. I have a little DNS server here in my house because why not? And I dumped all the queries for a day. I have a few kids, so I had a good mixture of school-based things, their class live calls, all their assignment research, my wife's work, her video conferences, and of course my lookups and the family's entertainment, email, and assorted, general queries. This worked out to about 92,000 queries of what I think a decently normal family would look like. I uniqued the list and stripped everything except the domain from the logs and wrote some bash scripts to run on my virtualization cluster. These queries were sent to the production servers in a few ways. The first was to run the list back to back, one query after the other as fast as I could send them, but waiting for each of the previous to finish first. The second way was to group them in random groups of less than 5 domains and bulk the transmissions and send them together. And the third ran a copy in for each available core thread and issued its portion of the list sequentially, waiting for each to finish in its own list before proceeding. And the last way was to make one request, same request, as many threads as the box could take for a single domain, just to throw as many queries per second as I could. So why would I send the queries one after another and wait for the return? Yeah, that's a great question. Thanks for asking. The DNS portion of a DOH request and return is a small portion of the total volume, and the work to produce the response, we all know how DNS works, is small compared to the HTTPS encryption, setup, and teardown. So by making each query set up a new session, this would drive load up and mimic what a non-bulk client streaming queries at a DOH server would look like for us. Say if you wanted to load up a DOH server, which is exactly what I was trying to do. So I ran these sets for an entire day, over 24 hours actually, initially starting by pointing at the load balancer, but moving to one backend member to put as much stress on an individual member as I could. At its peak, I was generating high tens of thousands queries per second pretty steadily, and 100,000 with some tuning, far more than a standard household would make in an entire day. And that's per second. This should be a decent amount of load, right? For to get those kind of tests, to get my timing, to be able to look at those kind of pieces. It should be noted that when I started to get into the high query rates, my poor firewall started to blow up, and it did have to be reset a few times. The graphs here you see puts three cert types next to each other, with the y-axis being setup time over 3.3 million queries per cert type. Obviously lower is better. It's less time to complete a query. And the error bars are the interval to give you some idea of variation. Because the setup and teardown of the session, this is what I was referring to in the last section, is the majority of the time in the session and load on the boxes. Would the cert type change the load profile, timing, and whatnot for a given server or for a client? Well, this is kind of the testing we did to find that out. The encryption setup will have a lot of variation depending on what hardware. If you decide as an ISP you want to go out and deploy DOH, that setup will have a lot of variation depending on what hardware you have deployed, what processor extensions are available, what kind of software you're deployed, and whether they use those extensions, as well as the other hardware in the client, offload cards that are performed either inside the server or maybe at a load balancer level. So there's a lot of free variables here. So this was an idea to compare them in a similar manner. When you take DO53 and wrap it up in DOH, you have additional lefting. That horsepower has to be somewhere. And so obviously it's heavily dependent on the certificate, the server, and the client. So we chose certificate cipher types and offer sequences from the currently advised list and tested 3, which you see here. I've taken the scales and numbers off as they were related to the test. It overlays a few tests and were generally not helpful in this context, but the take home here is that there was about a 10% difference in the session time, depending on the cert used, 20% total across the 3 we tested. The tests were run to the tune of far more queries than I did before, tens of millions of queries. Much in the same way the last bit of load testing was done, but these were all captured for time and session setup, etc. And were run sequentially to make sure that the setup and teardown were very pronounced. I didn't put the types of certificate there, as the timing, as previously mentioned, is heavily dependent on the machine, hardware, software stack, what extensions, etc. But what I do want to point out here is that testing is needed. You need to change those parameters and make sure you're using the best setup for your needs. There are lots of reasons to use a heavier encryption mechanism for some users, lighter for others, and that's a decision that people need to make. Just be aware of how much variation there is. From type to type, you'll note that the best of each is worse than the worst of the next best. So there's huge amounts of change here as we change cert type. So definitely something to, as a take home from a lesson learned. Huge shout out to Mr. Meleschi here, as he was the one that implemented most of this in the environment. As the underlying OS for these servers is Linux, there was a bunch of stack tuning that we performed, although Mr. Meleschi did all of the actual configuration. This is another area that is heavily environment and hardware dependent. However, it absolutely needs to be done. The largest gains were seen when file handle increases and of course network stack tuning were applied, as seen in the graph. The peak and subsequent leveling off, I believe, were the result of back pressure to the clients, resolving as they retried, and then as the new steady state was achieved. Without going into exact numbers, it's obvious that the rate was approximately doubled. This means that twice the number of clients could be served from the same hardware, software combination for effectively $0. As engineers, it's nice to be able to point to these things. It shows the importance of good configuration and obviously the amount of money that it does save. So where to look? File descriptor limits were the biggest change that helped with load. Total clients were big, and that configuration will depend on the DOH server that you're using, and obviously the hardware that sits in front and behind these. Linux network stack tuning was great. It did not have as much change as we expected or hoped. I believe that's because these sessions are very short-lived and there's no large flows created. So as all of these are environment dependent, obviously more testing, monitoring, yours will be different from ours, but any good tuning guides and any best practices are obviously going to make a huge difference. At this point, I'm going to turn this over to Mr. Jason Weil, who performed much of the field testing.
Awesome. So my name is Jason Weil. I'm a member of the emerging technology team here at Charter. I've been in cable for many years, but I'm new to Charter as of May, which is kind of bizarre, which means I've worked with a lot of people I've actually never met in person. The joy of 2020. One of the first projects I started on was the DOE trial. My thinking here was that it was going to be interesting to see a new technology being trialed on the Charter network. Then I also figured out there's policy work as well, which is always fun. So we actually updated our DNS policy and put that online after the hundreds of signatures needed to get it on there. But it's good that now we are now transparent about what we do with our DNS data. Right, let's get into this. So the first thing we did was build out a platform. Actually, two independent platforms or clusters. One in California, DO01.spectrum.com, the other in Texas, DO02.spectrum.com. The goal is to start testing each cluster independently, and then move into an Anycast model, which we have actually done fairly recently. So now DO01 and DO02 actually both resolved to whatever is the closest cluster by routing distance. Each cluster was slightly different from a hardware perspective, and that each had its own load balancer vendor. So we could trial a couple different load balancers against each other. The current trial setup for both clusters has the DOE TLS sessions terminating on the servers. In the future, we plan to do some testing with other TLS deployments, which I'll talk about at the end.
Sorry to interrupt, Jason. Your slides are not full screen. Do you want to make them full screen?
Let me do that. Better?
Yeah.
Okay, great. Thanks for that. Oh yeah. So and then as Todd mentioned previously, we did have to implement a new HTTPS based health check that looked for HTTP status 200 responses in order to get a pass from the load balancer to the servers. All right. So now I'll talk a bit about our inclusion in the Chrome same provider auto upgrade trial. So Charter began participating in the Chrome trial as part of Chrome 87 release. One of the key benefits we were hoping from participation in the trial was A, to generate significant DOE traffic to our trial platform, and then B, also see how the Chrome client performed against the Charter trial platform. And we were quite happy with the results we retained and are still obtaining. Quick shout out to Eric Orth and the team at Chrome for setting up this trial and letting us participate. So the original thinking is that we would receive a limited number of Chrome users hitting our DO platform because the majority of users with a router in their home network are getting a local resolver with an IP address of the router itself, which is typically a IPv4 RC1918 address. In our case, for a lot of our routers, it's 192.168.1.1. So this address will not be updated to the DOS to our DOS servers for Chrome users, receiving that. But thanks to RC 7804, the IPv6 requirements for home routers that we worked on a couple of many years ago. It was also included in the eRouter spec that we deploy on cable internet gateways. There's actually two must requirements that impacted this deployment. L10 and L11 for LAN requirements called for the inclusion of DNS IP addresses advertised on the LAN for both DHCP-v6 and IPv6 RA options. Well, guess what? The addresses advertised to clients on the LAN were not link local or ULAs, at least not in our case. In fact, these were the public IPv6 Anycast addresses of our classic DNS platform. And these are on the auto upgrade list in Chrome code. So voila, we have DO traffic thanks to Chrome.
So Jason, this is the timekeeper. You have about 5 minutes before Q&A.
Perfect. Thanks. Let's see. Okay, on this chart, you can see we were plodding along quite fairly low queries per second rate, which was wonderful for initial testing. We want to get the kinks out of the system. The platform was open to the public at this point, but there weren't enough public people using it. Well, they were using it, just not in quantity. But then on November 17th, when Chrome started pushing its 87 stable release, things got more interesting. We quickly went from hundreds of queries per second to over 10,000 queries per second, which was fun, good to see. One of the internal goals was to hit 100,000 queries per second on the platform, which it took a while, but I'm glad to say we crossed that threshold, and we have good data now to work from. So I thought I would give I thought I'd include the slide because I found it interesting to see what happens when CPU load starts to peak. This was made easier by actually limiting the number of cores into just a few boxes, so we could actually get to that 100% load. I'm sure others have actually seen similar results in the past, but in the queries per second graph in the top right there, you'll see that queries are ramping up nice and smooth, and then they just stop, and then you get this nice sawtooth pattern with a clear top, which makes sense because you can only serve what you can serve with your CPU. What's more interesting also for me from being a long-term networking guy is the networking graph at the bottom right there, which shows a significant multiple times peak in traffic. And it turns out this isn't like malicious traffic. This is just DNS clients being DNS clients and aggressively sending retries, which generates quite a deal of excess traffic. So I guess takeaway there is, don't max out your CPU. And if you do, plan for a lot of new network traffic that you didn't have before. Let's see. All right, last slide. So finally, our work is obviously not done. We have lots more testing and engineering to do, including work on improving the platform performance. Obviously with DO, you have more overhead with HTTPS and TLS over TCP compared to classic DNS over UDP. So now the question is, how do we improve the performance to get closer, obviously not on par with our DO 53 production platform performance? So some of the things we're going to look at are use of hardware to offload TLS on the servers themselves, and use of the load balancers to offload TLS sessions, among other options that we can look at. And we also want to test the new mechanisms being developed, and we're working on with the IETF and the ADNS or the ADD group, the Adaptive DNS Discovery Group, including use of new DHCP v6 and RA options to advertise the DOS servers, and also interested in understanding the impact of service binding records and HTTPS records, which we will hear more about tomorrow as well. And on that, I think that's the end.
Thank you, Todd. Thank you, Jason, for the presentation. The questions would be answered by Todd, Jason, and Ricardo. The first question that we have got from the Q&A is, what plans do you have to test defenses against DNS-specific DDoS attack, such as general query floods, non-existent record attacks? This is a question by Roland Dubbins.
I can help take that one. So to date, our software has some mitigation ability built into it from the vendor, but it was missing a few things. So we decided to implement rate limiting for the, for example, NO not implemented records. In addition to all records, we implemented a very strict rate limiting. One of the things we did notice when we did stand the cluster up, as it is a publicly available cluster, is that quote unquote bad actors did find it and did attempt to use it for any lookups against some large organizations. And we nipped that in the bud as soon as we noticed it. Other than that, rate limiting. Rate limiting is really where we're looking at mitigating most of these sort of attacks in traffic.
I don't see any more questions in the Q&A. If anybody wants to ask a question, please raise your hand. We still have a few minutes for the Q&A.
I think we have a raised hand from Paul and Brett.
I'm not seeing his hand. Yes. Paul.
Olivia, are you asking me? This is Paul Hoffman.
Yes, please go ahead and unmute yourself and you can answer the question.
Okay, this is Paul Hoffman from ICANN. So Todd, I was interested in the certificate slide, even without good axes. How did you change, what was the differences between the certificates? Were they different signing algorithms or different CA backends? That wasn't clear to me. Thank you.
Thanks for the question. They were different signing algorithms. They included different offer packages, etc. So this was based on the recommended types today, how strong they are and what they were signed with, etc. The software that was being tested at the time didn't include any CPU extension use, and so we were interested to see what differences those would make, and so obviously they were quite large.
Yes, it would be wonderful if you could publish just that information. That will obviously short circuit a lot of problems that other people have in the future. Certainly. Thank you for the suggestion.
We have a few more questions on the Q&A. First question from Peter Lexis. You have different vendors. Are these closed or open source?
I can take that question. We have not disclosed which vendor we are using for production use. However, we have multiple of all types in testing. So yes, I think is the answer to that one.
The next question is from Eric Klein. Any data about use of TFO and TLS early data?
I don't believe we have any data on those items. Jason or Todd? No.
We are starting to gather lots of TCP data, though, that it would be of interest for server tuning, but yeah, not those yet.
Thank you.
I think Brett Carr has raised his hand. Brett, do you want to ask your question? You can unmute yourself.
Yeah, it was just a quick comment rather than a question, actually. It was a really interesting presentation. Thanks, guys. It was really the thing that you mentioned at the end of the slides about future plans to test the TLS termination on the load balancers. I'd really like to hear about that when you've done it, because we actually do it that way already now, and we did it that way first. So, but our volume is much less than yours, I think. So, but you know, in the future, I'd really like to hear about that.
Absolutely. I think the take home there is that when you add HTTPS, there's obviously horsepower that has to be added. It has to be added somewhere, and kind of figuring out where the best place for that is just requires more testing.
Yeah, thanks.
I think we have time for just one more question. One last question from Anthony. Where do you expect your DOE traffic to originate besides Chrome mentioned in the talk?
So moving forward, once this is fully deployed in the network, which is going to take a little while, we've got a few bugs to work out. But the expectation is that it's going to be open to the world, but our subscribers, charter subscriber spectrum, will essentially be auto upgraded to DOH through in-browser pushes and /or operating system pushes as operating systems go into DOH as well.
I think we can expect to see something from Microsoft, but I'm just guessing there soon.
iPhones, Android phones, all of those things are going to start auto upgrading once the service is available in our network.
I think we are just about right time to end this talk. Anybody has any questions, please feel free to ask them in Mattermost workshop channel. So thank you, Jason. Thank you, Todd. And thank you, Ricardo, for answering the questions.
You're welcome.
Next, I would like to invite Andrew Meshkov from AdGuard to talk about their experience deploying the first ever implementation of DNS-over-QUIC. Please go ahead, Andrey.
So my name is Andrey, and I'm a CTO at AdGuard. And recently we launched the first ever public DNS-over-QUIC resolver. And so today I'd like to tell you more about it. But first, let me please start with a very short introduction of what we do and where DNS-over-QUIC was deployed. So AdGuard is originally a content blocking tool, but we also develop a number of DNS-based solutions. First is AdGuard DNS. This is a public DNS resolver. AdGuard Home, this is a home DNS server for personal use, and AdGuard apps, mobile apps mostly. They also provide DNS filtering and encryption capabilities. And so all of them got DNS-over-QUIC support a month ago or so. A few words about AdGuard DNS. It was launched a couple of years ago, and well, it's kind of popular among people who want to get some content blocking on the DNS level. Currently, AdGuard DNS, it is here are the stats. So it's about 100,000 RPS. And as you can see, a considerable part of it is encrypted. So the largest part is DNS over TLS, which comes mostly from Android devices. There's also DNS over HTTPS, DNS crypt, and finally DNS over QUIC, which this slide is a little bit outdated. Actually, DNS over QUIC seems to grow, and currently it's already 1.5%, which we think is not bad because it is clearly indicated that this is an experimental protocol and still people opt to use it. So this is just an introduction. Now let's talk about DNS encryption in general before I will start to talk about DNS over QUIC. And so let's talk about different protocols, pros and cons, and we'll start with the ordinary normal DNS protocol. It is the fastest of all. It's light on resources, and a resolver like ours can handle this load like on a single, not very expensive server. However, there's one fatal flaw. There is no encryption at all. Next, DNS crypt. I think it was the first commonly used DNS encryption protocol. And well, it's not bad. And sometimes I missed the time when it was the only one. Performance-wise, it is almost as fast as the normal DNS, but unfortunately, it has a couple of important flaws. And the most important one is that it uses a non-standard encryption. And unlike TLS, it was never seriously audited. And well, it is quite easy to detect and distinguish from other traffic. Then there are DNS over TLS and DOE that are rather slow compared to regular DNS. They might look fast enough in tasting environment or when you have good network connection, but in the real life, especially on mobile devices, drawbacks of these protocols become clear. For instance, a pretty slow TLS handshake that happens every time when the network changes, or a single lost TCP packet that delays all other DNS queries. And besides that, they're obviously heavier in terms of bandwidth, mostly due to the heavy handshake process. The server has to send the full certificates chain to the client, and even though there's TLS session resumption, it doesn't fully negate this problem. And now let's talk about QUIC and what is the difference between QUIC and TCP plus TLS stack. QUIC originally was supposed to solve most of the issues that are specific to HTTPS and to TLS. And here's what it helps with. First of all, QUIC speeds up the initial handshake. It is supposed to solve the head of line blocking issue. And also it provides an interesting mechanism for so-called connection migration, which allows to use the same connection even when your IP address has changed. Let's take a look at each of these advantages. So first, let's talk about faster handshake and how it's achieved in QUIC. Encryption and authentication are normally handled by a higher level protocol, well, TLS, and not by the transport protocol, so TCP. But QUIC changes this. As you can see on the slide, QUIC handshake combines the TCP-like three-way handshake with the TLS-like handshake. And again, as you can see on this slide, QUIC handshake can be completed fast. It requires a fewer number of packets because, well, let's take these slides. On the left slide, you can see a regular HTTPS handshake. First, there's a three-way TCP handshake. Then there's also TLS handshake, also three-way. And now, only after that, the first DNS or HTTP request is being sent. And on the right side, you can see that in the case of QUIC, it is combined, so there are only 3 packets instead of 6. And so all in all, it is faster. Well, should be twice faster. Second issue I would like to talk about is head of line blocking. So the current DOE standard tells us that DNS over HTTPS is supposed to use HTTP2. One of the main advantages of HTTP2 over older HTTP is multiplexing, which means that you can multiplex different HTTP requests inside the same TCP connection. Unfortunately, this has an important downside. Since multiple requests and responses are transmitted over the same TCP connection, they are all equally affected by the packet loss, which happens rather often on mobile devices. So even if just a single DNS query was lost, others will also be affected. The client or server will have to wait until it is retransmitted, and only then they will be able to continue processing other queries. Well, this is essentially what is called head-of-line blocking. So let's see how QUIC solves this. QUIC also supports multiplexing, just like HTTP2. And just like HTTP2, there are streams, there are frames that go through those streams. But there's a huge difference. QUIC streams are delivered independently. So even if packet loss occurs and affects one of the streams, other streams are unaffected. And in the case of DNS-over-QUIC, client initiates a new QUIC stream for every new DNS query. Therefore, if one DNS query was lost, it does not affect other queries. Last but not least, connection migration. This feature allows QUIC endpoints to migrate connections to different IP addresses. For example, a mobile client should be able to migrate QUIC connections between cellular data and Wi-Fi. The simple example is when you leave a house and you disconnect from your home Wi-Fi and start using your start using cellular data, the QUIC connection can stay intact. Not every time, for instance, not in our case. I will tell about this later. But in theory, this is possible, and this is achieved by introducing a concept of a connection ID carried by QUIC packets. So endpoints can use this ID to track connections that they are responsible for without the need to check the source IP ports and destination IP and ports. Now I would like to talk about DNS-over-QUIC versus DNS over HTTP3. I've heard a couple of times that DNS-over-QUIC makes little sense because DOE will receive QUIC support naturally when it's upgraded to HTTP3. And to be honest, to me, it sounds rather strange. To put it simple, let's take this analogy. Imagine you want to get to a different city. You can travel by train, you can travel by car, or you could travel by train with your car. Granted, your travel will take pretty much the same time, but I just cannot understand why would you need to bring the car over there? And what's the point? In this analogy, obviously, train is quick and car, I guess, I think you can guess. So if we compare DNS-over-QUIC and DOE3, both of them use QUIC as an underlying transport protocol. HTTP3 adds HTTP on top of it, which means it sends and receives HTTP headers alongside every DNS query. And the problem is that protocol-wise, it adds no value. One could say that you can benefit from HTTP caching, but why would you need to complicate things and use it instead of the standard DNS cache? And besides the overhead of carrying HTTP headers with every DNS query, it also adds more data points which can be used to fingerprint clients. Let's take a couple of examples. For instance, different DOE clients, depending on the implementation, may use different headers order. That's +1 point. Different DOE clients may use different TLS properties. And also HTTP caching provides some tracking capabilities. For instance, e-tag tracking could be used just as cookies are used now. And that's why DOE clients should be careful with that and simply not implement that. And all in all, the only real benefit of DAO 3 is that the existing DAO clients will get its support naturally with little effort. But that seems to be all. And well, it just doesn't seem as elegant as DNS-over-QUIC to me. And now I would like to talk about DNS-over-QUIC implementations that we made at Edgard. So the first one is we have a core DNS fork that we use at Edgard internally. And it's open source. Everyone can just take it and use it. And on this slide, you can see a sample core DNS configuration that is enough to run a DNS-over-QUIC resolver. As you can see, the only thing you need is a valid TLS certificate and a private key. Then there's also another tool that we developed at Edgard, which is called DNS proxy. And it also got DNS-over-QUIC support, and it is also open source. This is a simple command line tool that allows to run a forwarding DNS server, just like DNSMask, with the only difference that it supports all kinds of DNS encryption on both ends. It could be an encrypted DNS server, or it could forward DNS traffic to an encrypted DNS resolver. And it supports all kinds of protocols, DNS-DAO, DNS-over-TLS, DNS-over-QUIC, you name it. And also it is written in Go, and you can also use it as a library if you would like to do some coding. And then there is and then there is Edgar Home, the personal DNS server that also got DNS-over-QUIC supports. It got it naturally since it uses DNS proxy that I mentioned before. And we also developed some DNS-over-QUIC clients. So again, DNS proxy, again, Edgar Home, I just talked about them. And also there's a DNS libs library that we also use in Edgard. We use it in our mobile apps, which is written in C++, and it also allows to use DNS-over-QUIC. And the last one is DNS lookup, a very simple NS lookup-like tool that supports all kinds of encryption protocols. And now I would like to quickly talk about existing QUIC implementations. First, the one that we use for our Go for our tools written in Go is a library called QUIC Go, which is not bad. The only downside is that it does not support connection migration yet. And for C++, we use ngTCP2, which is also very works very well, and we're quite happy with it. On this slide, I missed to mention Quiche by Cloudflare, but actually this is a very solid option, and we experiment with it at Edgard. And so far, it shows better results than the tools that use QuickGo in terms of performance. So I can recommend it easily. And about current issues. Current issues of DNS-over-QUIC is that, well, connection migration is not supported by Edgard DNS. This is kind of our issue and not DNS-over-QUIC issue, but I would like to mention it anyway. There are two problems with connection migration. First of all, it's not yet implemented at QuickGo. Well, obviously, this is a problem. But then there's another problem. At Edgard, we use ECMP to balance load between servers in the same location. And ECMP is not compatible with connection migration as well. I hope in the future this will change, and there will be routers that are able to handle quick traffic. But at this point, for now, most of them use IPs, so client IP and port to load traffic. and there's a chance that packets may be when the client changes its IP. There's a chance that the packet will be routed to a different node that is not aware of this connection ID, of these clients' connection ID. And finally, QUIC and DNS-over-QUIC are still drafts. I really hope that this will change, but well, for now, it is not final. It is not a final standard. And a few words about users' feedback. So what we get from our users, they seem to be pretty happy, and looking at the numbers and on the server load, I see that more and more people try DNS-over-QUIC and choose it over the alternatives. And also, it seems that DNS-over-QUIC is not really blocked, and it works pretty well and reliably. And the most positive feedback we're getting from people with mobile devices. So it seems that it does provide advantage over DOE and cellular data networks due to faster handshake, for instance. And one more thing that, again, is not mentioned on this slide is that I've heard at least about one public DNS resolver that is going to implement DNS-over-QUIC in the nearest future. So I hope that the prospects are bright for DNS-over-QUIC, and I'm happy with it. So that's it. Thank you very much for your attention. I'm ready for any questions.
Thank you, Andrey. That was a very interesting presentation. I would like to remind the audience to fill the poll, because this is your chance to fill it. It will pop up like in a couple of minutes right after presentation. Andrey, we have a few questions for you. The first question is from Roland Dubbins. His question is, what is your view of the perceived inevitability of DO3 versus DNS-over-QUIC? Isn't DNS-over-QUIC already doomed to the momentum behind DOH generally?
Well, I think I've answered it when I compared DNS-over-QUIC versus DNS over HTTP3. And you see, things are changing rapidly. And 2 years ago, no one heard about DNS encryption, and now it becomes more and more popular. And at least I can hope that people will choose a more elegant solution, which is DNS-over-QUIC over DNS over HTTP.
We have one more question from Andrey. Andrey is saying that I'm confused about DOQ versus DOH3. Wasn't one of the arguments for DOH that you would be able to mix your regular HTTP traffic with DNS traffic to prevent snooping and blocking?
On one hand, this is true. On the other hand, DNS-over-QUIC can also be as hidden as DNS over HTTP, because both HTTP3 and QUIC use the same transport. And second, it's not that you mix it. So as we see right now, there are a couple of popular encrypted DNS resolvers, and each of them can be easily blocked. I do not see any actual problem with blocking DNS or DOE or DNS-over-QUIC or any other encrypted DNS protocol. This is not something that can be easily fixed just by encrypting traffic or using the same port as HTTPS.
Thanks, Andrey. We have one last question from Puneet Sood. We have very little time left. Puneet's question is, why did you write your own DNS proxy compared to using DNS dist and extend it to support DNS-over-QUIC?
Because, well, there are multiple reasons. Because we prefer to have things under control and be able to extend it as we like. Because we use Go, and I'm not sure if DNS dist also is written in Go. And well, it is not a new product. It's not that we wrote it a month ago. It's been a couple of years, and I'm not sure that when we wrote DNS proxy, there were a lot of DNS encryption tools like that available.
All right, that was our last question. Thank you, Andrey. And now we will take a 15-minute coffee break, and we'll all be back by 20:05 UTC, followed by the final round of presentation for the day.
Thank you.
Welcome back from the coffee break. Now I think we are starting 12:05 UTC. We'll see the final, some of the final rounds of presentations for the day. And I would like to now welcome Moritz, Müller, and Jins to talk about the impact of post-quantum cryptography on DNSSEC. Go ahead, Jins. Yes.
All right. Thank you. Welcome to the presentation on the impact of post-quantum cryptography on DNSSEC. This has been joint research together with folks from University of Twente, TNO, and Anode Labs. And the goal of this presentation is basically to show you a bit which kind of challenges we might have to face when we have to move to quantum safe algorithms in the future. So when the time when quantum computers are there and that might break DNSSEC. Next slide, please. So You've probably heard about this threat of quantum computers and the threat that they possibly are able to break most of the public key cryptography that we're using today on the internet, including the algorithms that we currently have standardized for DNSSEC. Luckily, at this point in time, there are currently a bunch of algorithms that are being assessed by, among others, by the NIST standardization body. And these quantum-safe algorithms could be applied to DNSSEC as well. However, many of these quantum-safe algorithms have quite different attributes than the algorithms that we use today, and therefore there might be a bit of a challenge to apply them to DNSSEC. And the goal of this research was, okay, are there quantum-safe algorithms that can be applied to DNSSEC? And if not, what would we have to change in order to make that happen? But first, to discuss that, Jins will briefly introduce you to some of the principles behind these quantum-safe algorithms.
Yes, thank you, Moritz. We're used to RSA, elliptic curves, and discrete logarithms to build our public key cryptography. But as Moritz already mentioned, we'll have to replace them with. And to get a bit of an idea what we're replacing them with, going to give a small introduction, nothing technical. Over here, it's too late for any technical details. So let's go on, let's see. A quantum computer threatens current cryptography in two ways. The first way is by an efficient search algorithm, which is, for example, interesting for symmetric ciphers. There's a fairly straightforward way to deal with this, just double the key sizes. However, a more severe step is needed to counter Shor's algorithm. This gives an exponential speed up in finding solutions to or breaking RSA and discrete logarithms and also elliptic curves. So we need something new. We need another form of cryptography, post-quantum cryptography. When do we need it? Well, perhaps in the 2030s. A couple of weeks ago, I heard a talk, someone estimated 2035, give or take a year. Could be earlier, could be later. That's one of the big unknowns and also one of the threats to all kinds of current cryptography. Okay. What are we looking for? We're looking for algorithms with the same structure as the current public key cryptography we use. We need a public key, a secret key, we need signatures, we need key encapsulation mechanisms, with the additional requirement that no classical computer or quantum computer could break it quickly. From a perspective of DNSSEC, it's the signature schemes that we're most interested in, and those we will focus on in this talk. As I already mentioned, NIST, as Moritz mentioned, NIST started the standardization process to find the best post-quantum algorithms to replace them. However, there is not a perfect candidate yet. Compared to, say, elliptic curves, there'll always be a drawback. Either it's much slower, the keys are much larger, the signatures get large. So ideally, one would wait for better algorithms to appear. However, the timescale doesn't allow us this luxury. We have to find solutions for our cryptographic needs. NIST started this process in 2016. Last July, they started the third round, which could be called the final round. There's still 6 signature schemes in competition, 3 as finalists and 3 as alternative candidates. And it's likely that one or more of them will be standardized. There are a couple of mathematical problems underlying these finalists, and I'll discuss them really briefly, just to get a vague idea. The first is multivariate cryptography. Here, the mathematical problem one has to solve is to solve a system of m polynomial equations in n variables. And there are 2 cases here that are relevant. The mathematics isn't really, but these 2 cases are. First, there are the key encapsulation mechanisms, and these are hard to construct. And these are also, to a certain extent, what gave multivariate cryptography a bad name. It's unreliable. On the other hand, there are signature schemes, which vary in their instance of the problem, and those are much easier to construct. So signatures based on multivariate cryptography are a good option. And this also can be seen in the submissions to the standardization process. There are hardly any key encapsulation mechanisms based on multivariate cryptography. And in round 2, there were none anymore. Whereas signature schemes, one of the finalists and one of the alternative candidates are actually multivariate signature schemes. The second is most famous. It's lattice-based cryptography, and it offers, everything and much more. Compared to what we're known, however, all the sizes get much bigger. So signatures will get bigger, keys will get bigger, and we'll have to find a way to accommodate that. The underlying problem is that you get an ugly lattice, say these two red factors, and you have to find an integer combination that yields you either the blue factor, which would be then the shortest factor problem, or a factor closest to the green dot, which would be the closest factor problem. The last one is hash-based cryptography, which is quite remarkable in that it doesn't really require a mathematical problem, but only a secure hash function. Well, those we can build. It's signatures. You can only build signatures from them, and they're quite typical. They have very small keys, but very large signatures, which make them somewhat unattractive for DNSSEC. Well, to prove my point, I have made a very small table with some of the algorithms submit to NIST competition in round 2. And the only thing I would like you to see is how different these numbers are. There's a huge variety of large private keys, of very small private keys, of, relatively compact to even small signatures, but also extremely large signatures. For reference purposes, there are the elliptic curve signatures that are, a current standard. And these cycles on the right are cycle counts I picked from the technical documents. However, these should be taken with a grain of salt. Back to Moritz. I'll stop sharing and give you control of the presentation.
Thank you. Let's hope this works as well. Now you should be able to see my full screen. Is that correct?
Yeah, looks good.
Yeah, great. Thank you. So now that we hopefully have a rough idea of how these quantum safe algorithms look like and what their attributes are, we can start thinking about, can we apply them to DNSSEC as well? And therefore, we first have to understand a bit what kind of limitations do we have in DNS and DNSSEC. And here we think we have especially 3 limitations. The first one are key and signature size. As we've heard today already, messages larger than 1,230 bytes or maybe a bit bigger often cause fragmentation. So we probably do not want to have signatures which are larger than that. Also, we know that DNSSEC and DNS in general is often or sometimes misused for distributed denial of service attacks because of the amplification factor. And if we would have keys or signatures which are very big, then this amplification factor makes DNSSEC again very interesting for these kind of attacks. Then we have validation performance. We've also heard today that resolvers can resolve thousands of domain names per second, and potentially, if DNSSEC is becoming more attractive at some point, then they might also have to validate thousands of signatures per second, and I think some resolvers already have to do that. And last, when we want to sign records, then in the worst case, we might even sign them on the fly. So then we also need a very good signing performance. based on these three limitations, we derived three very basic requirements, which are probably depend a bit on your use case a bit, but we think they are a good starting point to pre-select potential interesting algorithms. The first one is that signatures should be not bigger than 1,230 bytes. And I will explain a bit later why we think that keys might be able to, it might be possible to have bigger keys. Validation performance should be at least 1,000 signatures per second. Again, just a rough number, and signing performance more than 100 signatures per second. So based on these requirements, or especially the first requirement, we did a pre-selection, and we only had a look at algorithms in the last round of the NIST competition that had signatures smaller than this size. And the first algorithm that we had a look at was Falcon 512. Falcon 512 is a lattice-based algorithm, and on first sight, it has quite attractive attributes. The performance is quite good. This is based on a measurement on a test machine of ours, and just should give you a rough idea as well about the performance. And the keys and signatures are not very big. But already if we would have to put two keys in one message, or maybe multiple signatures, as we have, for example, with NSEC records, or NSEC responses to non-existing domain names, then we already have multiple signatures, and this increases the response quite a bit. In contrast, we have two multivariate schemes here as well, which have very, very small signatures. They are on par with the algorithms that we use today. The performance seems to be also quite okay. But the public key is very, very big. It's even that big that we can't put it into regular DNS messages anymore. So how can we still apply, could we still apply these algorithms in DNS and DNSSEC? So for the increase in signatures, we could hope for an increase in TCP support, and then as soon as someone would query more than two signatures, the resolver would probably fall back to TCP, with all the disadvantages that come along with that as well. For the keys, especially the keys which are too big to put into the DNS message, we could have a look at, for example, out-of-band key distribution, so that we refer the resolver, the validating resolver, to another source to fetch the key. Or you could, for example, also split the key into multiple DNS records, DNS key records, which then has the problem that the resolver would have to send multiple DNS messages, which increases the chance of failure as well. If we would run into problems that validation performance is too low, then we could reduce the time that we have to validate, for example, by increasing the TTL for records, but this also might not be feasible in some scenarios. And in general, we might have to look into zone-dependent algorithms. So for example, some zones like the root might have higher security requirements at some point, and they might have, they might need to use algorithms with a higher security level than the ones that we've discussed today. So based on these observations, we can probably see that applying quantum-safe algorithms to DNSSEC will not be that easy. And we probably have to do more research and to do some more testing to actually implement some of these proposals, like out-of-key distribution, to actually understand what this means in a realistic environment. Also, what we've seen in the last months already is that things still change quite a bit in the quantum-safe algorithm world. So we've seen that there were some articles published about potential security issues with some of the algorithms. So we can see that there's still a lot of going on here as well. And this might also force us then to look at other approaches as well. So for example, hash-based algorithms or combined with Merkle trees might be an option. And some of you might have read an article by folks from VeriSign where they discuss that as well. I can later put the link of the article in the Mattermost chat. In general, we also have to keep in mind that rolling to the algorithm will take time. And this is why we believe it makes sense to have a look into transitioning to quantum safe algorithms now already, because we've seen in the past from our measurements, from within the community, that even now there are still some algorithms around which are not secure anymore, and transitioning to more secure algorithms just takes a lot of time. We've summarized our findings in a paper, which is not shown on my slide here correctly, but I hope you can see it. And with that, I would like to ask you if you have some questions.
Thank you, Moritz. Thank you, Jins, for the presentation. We have one question. Before that, I would like to remind the audience to make sure that you fill the poll that will pop up on your screen. Going to the question, we have a question from Joey Salazar. To clarify this encapsulation of keys, is it meant to be an end-to-end encryption of the keys? If yes, is it meant to also be used point-to-point fiber connections? At the IETF QR working group, they said currently 2p2 fiber connections are planned to be used for QKD quantum key distribution, but this is not encrypted by design, even though there is awareness of potential attack at that connection level.
Yes, go ahead.
I think I can take it. The NIST post-quantum cryptography competition does not really deal with quantum key distribution. That uses quantum principles to distribute keys. We're not doing, well, here, none of this is done. The key encapsulation mechanisms I refer to are the replacement of key negotiation protocols that exist, for example, with discrete logarithms is a well-known example. For our talk, I've only mentioned them for completeness, but for DNSSEC, we're only concerned with signature schemes.
Thanks, Jins. We have one more question on the Q&A, and then I will move to the questions by the panelists. We have a question by Peter. When quantum computers exist, would DNSSEC be a primary target to break the crypto, or would there be other more low-hanging fruit?
I can, I guess, since in DNSSEC we do signing, I think DNSSEC will not be the first target here. We have signatures which are not that long-lived, which makes it not very attractive as a target. And also in terms of probably interesting secrets, there are other messages that are being transmitted via TLS, for example, which are more interesting. But folks are already also looking into how they can make TLS quantum safe as well.
Well, and to add to that, if I may, DNSSEC is interesting for another reason, not perhaps because it's the main target for an attack, but because it's quite a performing system. And as we've seen, these new algorithms have serious drawbacks, and whether they can deliver on the performance requirements that DNSSEC knows is really an open question. That's the reason to look at DNSSEC now already. Now there is still room to, respond to NIST and say, please consider DNSSEC and the requirements it poses on a new signature scheme. Once they've standardized, that may not be possible anymore, and other solutions for DNSSEC need to be found.
Thanks, Jins. We have one question. Paul Hoffman, please, you can unmute yourself to ask your question.
Thank you. This is Paul Hoffman. Actually, I also see Benjamin Schwartz behind me in line with the hands raised. So thank you for the presentation. Yes, it's good for this group to have fair warning. About 2 weeks, just Moritz, as you said, oh, things are changing quickly these days. About 2 weeks ago on the NIST mailing list, NIST itself proposed that it might slow down the choice of signature algorithm. That is, they said, oh, would you all like if we sort of extended out that one by by an indeterminate period of time to work on this more? And I think that that is actually a response to DNSSEC and other folks who are saying the properties here are pretty bad. There is also, as Jins just said, we're not the main target for this. It's really the key encryption folks. Those folks are the ones who, if you have a secret now that you want to keep secret for 30 years, you don't want someone decrypting it 25 years from now. Our signatures don't last that long. And so in the case that quantum computers that can attack our current algorithms, the classical algorithms, ever come along, and they may not. I mean, many of the people in the field are now predicting that maybe they won't. That we have the best chance of like, oh, okay, we'll change our signatures with 5 years warning. You can't previously unencrypt other stuff before. So I think we're much better off than the folks in the TLS world. Thanks.
Yes, thank you. And I completely agree. In the case of DNSSEC, it's more in question, well, can all the infrastructure be put in place within time? Then are there secrets that will get that old? So yes, thank you.
Thanks. Ben, you can unmute yourself to ask the question.
Hi. I noticed in your presentation that you seem to, in effect, be assuming, or at least hoping, that the most efficient, most suitable algorithms in the competition turn out to be essentially solid and eventually approved. And I wonder what your forecast looks like under a little bit less optimistic assumptions, where we don't assume that the most suitable algorithms are the ones that turn out to work. Is it time to break the 64 kilobyte limit in DNS? And do we need to rethink how we handle multiple signatures in the case where, or multiple key types, in the case where we have algorithms that we need to use, but that we don't have real confidence in?
I think these are two very good points. We now have looked in the algorithms that are most suitable for what we think should be in DNSSEC, but I think we, as I pointed out here in the last slide, we definitely need to look around whether we can also handle algorithm types that are maybe not that suitable for DNSSEC. But I think this is why we try to start this discussion now already, to be prepared if maybe then not those suitable algorithm will be selected at the end of the process. Yeah, when it comes to the DNS message size, I think this might be an option. I'm not sure how easy this is to work around this limit of 64 kilobytes. I guess this requires still a lot of research, but I think this might be also a good direction to have a look at. The same goes for the algorithm selection in case we have an algorithm that we don't trust. But I can't say anything about the chances of these changes to DNS to be successful.
Thanks, Moritz. We have one question from the attendees. Priya Mohan, please unmute yourself to ask the question. Priya Mohan. Please unmute yourself to ask the question.
Oh, sorry. So I unmuted by mistake. Sorry.
Did you have a question?
No, I don't.
All right. We have one more question in the Q&A. The question is from Alison Mankin. The question is, one point that 2013 Catacrypt workshop on post-quantum made was to do code signing and then be able to replace code bases such as DNS safely once there will be a once there's been a quantum break. What do you think?
Jins, do you want to take over?
Yes, I'm not entirely sure if I understand the question, to be entirely honest.
Yes, Alison Mankin, please unmute yourself to speak.
Yeah, hi, can you hear me? My point was that it's that when presented with several of these options, the Catacrypt experts, who are people who are, you know, with Diffie and Hellman and all those people, they said that they were advising people to focus on code signing with a quantum safe protocol, and then be in position to make changes later because we've at least signed our code, so we have more time to work on these problems. And I wondered if you thought about that point.
Well,
give yourself more time. Right.
Yes, I do not know if you're referring to code-based cryptography, which is indeed very secure and very competent, but it's mainly suitable for the key encapsulation, since signatures on that size become massive, if I'm not mistaken, or the public keys are massive. But
Jens, I'm really talking about simply having signatures on all of our code base, having quantum resistant signatures on the code base of all our stacks, for example, so that we do that first as a way of providing an overall insurance, because the code can't be tampered with, the binaries and so on can't be. If we have that in place, it gives us more assurance that we can replace algorithms later.
May I propose that you send me a question?
Yeah, sure.
Out of this conference, so that we do not pause the conference too long, and I'll be happy to think about it and answer it.
Okay, yeah, I'm not representing the people very well. Hellman was really big on this, but I don't think I'm representing it properly. Thank you.
Okay, thank you.
All right, thanks, Jins and Moritz, for that nice presentation and answering all the questions. If anybody still has to fill the poll, please go ahead and do it now. Next, I would like to invite Jeroen Massar for a lightning talk about hashed RPC. Please go ahead, Jens.
Good morning, evening, and afternoon for depending on where you are. Do you hear me?
Yes, I can, and see your slides too.
Perfect. Thank you. I'm Jeroen Massar. I'm giving this presentation as an independent because I've worked on this for a variety of customers of mine, which will come up in the slides. What this is about. So this is about hashed RPZ. So since the beginning of this year, there's a new law in Switzerland for blocking CSAM related domains. So child sexual explicit content.
Sorry to interrupt, Jeroen. We are seeing the presenter view, not the slides.
Then I need to give the other one.
Yeah, sorry about that.
No worries. There we go. So there's a new law in Switzerland since the beginning of this year. We were notified about this a couple of years back already, that would be coming for blocking CSAM material. The blocking is domain-based, so they just give a list of domains and we fetch it from SFTP server, which is a couple of RAR files which are password protected. So the standard solution will be to use RPZ, which everybody, I guess, here in DNS-OARC will know. Otherwise, find the references to at the bottom of this link to dnsrpz.info. And it's very simple. You just can say like www.badexample.net. You can CNAME to a dot, and that will annex domain it and thus block the zone. This is also being used in Switzerland by another law, but that is less sensitive. And that is for what we call the casino law. And that is basically for blocking casinos so that people cannot go to an unlicensed casino, basically. Of course, doing this kind of blocking will give you negative effects because, for instance, if you go to casino.example.com, but it has a the Weil example where you get redirected to a Weil on HTTP, which indicates why that page is being blocked. It typically mentions the standard text that the federal government, the Swiss federal government have defined. But yeah, with HTTPS, of course, which most casinos will be using, you will just get an SSL error. So it's not so very useful to block it this way, in my opinion. But the problem is if we get this list from the federal police with all these really illegal domains with rather explicit content, it will not be very good, because if you are going to debug, it might just happen that you will get to this list of domains. And also it will appear in backups and everything else. And thus what we want to avoid is that if an engineer that is maybe just trying to debug why a certain DNS server, one of the backends with recursors that has this list is giving issues, they might just stumble accidentally upon, well, explicit links. And under the law, under the text of the law, it is illegal to even have access to the link. And they could just say like, well, look, they have this link, so they probably access the material. And with this kind of content, that might just destroy your career. Your environment, your neighbors, they might not think about it when in the news it says, well, he had access to these links. And it will be very difficult to explain away. So to avoid that, I came up with a scheme called HardsRPZ. Although I heard already from people who saw the slides that, for instance, PowerDNS was doing a similar trick as stated at the last line using MD5. So it's not completely new idea. There's some new stuff in here, but not completely original. So what we do is we split the label, and the best thing to see it at is the example given at the bottom. We split the label, or the whole left-hand side, we split it into labels, and we recursively, basically, starting at the right side, we first hash the com part, or the TLD, then we hash the domain, and then we do the subdomain, and we keep on going till the whole left-hand side has been hashed in this method. And that way, the zone file that is being transferred to recursive with the RPZ when you do the AXFR will actually not be in clear text. So if you're debugging, you will see a list of, well, gobbledygook, and example will come later, that will not have anything actually explicit in there. So you cannot well, you can click on the link, but the link will actually not go anywhere. While if it was an explicit content, you would go somewhere that, well, would be illegal. So as we had a very nice crypto talk just now, I also believe in the mantra, don't roll your own crypto. I'm not a cryptographer. There are people who are, and they have done this research into creating a new hashing standard called Blake 3. So according to performance numbers that I ran myself also, and the slide, the performance number here on the slide, Blake 3 is very performant. It was definitely faster than MD5, and it's supposed to be a lot more secure. And the most important property that I use for this is that it can also be keyed. So you can add a key to it, and that will give you a better, more protection against verbose style attacks. So what we do is we take one key that we put in band. It is encoded inside the zone. So you get an _RPZ hash key .rpz.example.net. And the other one you configure in the configuration for the zone in your recursor. That has to then support, of course, this special hashed RPZ setup. And that will then distribute, for instance, these examples. We have, so for instance, w.example.net, you'll see that the output is quite long because we encode strings shorter than 4 bytes or 8 or 16 into hashes of 4, 8, or 16. So you can also recognize that .com in the two examples are actually encoded the same, and example.com is encoded the same, or well, hashed the same. But you cannot see that example is the same word in both because of the recursive hash that we do. Now, putting that together, what we did is we made a host, a VM at the moment, that actually fetches the list from FedPol, from the Federal Police. And we have restricted that heavily so that only 3 engineers actually can unlock the disk or boot it at all. And when it's booted and it has its credentials for doing the job that it needs to do for fetching the list and encoding the, encrypting the RAR files, you cannot SSH into it anymore. At least not to that level. So you cannot get access to the lists that are fetched. And yeah, so one thing is if we get this mechanism standardized, because that is what this talk is primarily about, to get input, then we might be able to ask the Federal Police to basically do this trick for us, and then we don't even ever have to see the clear text file, which would be very good. For that, I did, like our friends just now, we have an implementation of a Golang DNS server because it was something that we already ran for various purposes. And so it was, of course, the easiest to implement. Of course, this will hopefully lead to work where we will get standard implementations in the standard resolvers that exist and that everybody uses and loves, like Unbound and PowerDNS Recursor and Bind, of course. And not to forget. So we see a cache miss of about 10%. So we have a cache hit rate of about 90% on those boxes. And of course, then the 10% has to be also hashed. So there is a little bit of a performance impact. I still have to run the DNS-over-QUIC flamethrower tool over it to do some more performance hits, but it has been running since end of December in production, and it has been running fine. But we have heavily over-provisioned our boxes. So the future work will be integrate feedback from operators and developers. That's why I'm giving this talk, to get your input. Fortunately, because some people saw the slides, they already gave a lot of input. That's why we have a lot of backup slides next. And of course, to work on an ITF draft, if people find this an interesting thing, so that we can make it interoperable. And then, of course, to make the patches for Unbound, PNS, Knot, and for Bind 9. More optimizations and testing, and then hopefully to convince the Federal Police to generate this RPZ file for us. So yeah, that is the primary goal, to keep our engineers safe. There are some side effects also. If you are an RPZ provider, you could provide, for instance, a list or an RPZ zone that is hashed. And so somebody could not check if certain links are on it, or steal the list because they don't know what's in there. So you can easily hide a testing node in there, which is what we also do. We always have a test label in a zone for ourselves so that we can check if the process actually works. So I'm opening up to questions.
Thanks, Jeroen, for the presentation. We have a couple of questions in the Q&A section. First question is from Brian Dickinson. For RPZ, what about returning signed RPZ responses and publishing the public key for that RPZ zone? This might kind of look like DLV all over again, but at least it would allow the clients to validate the blocking results, including possibly the walled garden.
Correct. Yes, that is the intention of that part. Does that answer the question, actually?
And I think, Jeroen, if there are any discussions, they can be done in, like, the Mattermost workshop channel too.
Yes, absolutely. Don't hesitate to ask questions either in the by email, by Mattermost, or by the GitHub. You can also file tickets in the source code repository, because there is, as I have here, we have running code, of course, for this. So there you can also file questions.
Okay. And we have a few more questions. Next question is by Paul Vixie. How do you hash left-hand sider triggers?
That is a very important, very good question. The trick is simply that you're hashing the label, and triggers will be well handled like normal RPZ. It's just that the label in the zone is different.
Thanks, Jeroen. The next question is by Robert Edmonds. Wouldn't every commercial RPZ feed provider want to use hashed RPZ to keep their secret sauce secret?
They will probably want to do that, yes. And that is, of course, partially in concern because you cannot validate this list. And of course, if we're talking about, well, lawful blocking where the law dictates it, it becomes a bit tricky if you think that maybe they put a political party in that list. And that, yeah, that is, so you need to have maybe like an oversight committee, especially if you are talking about federal blocking or yeah, government blocking to overcome this.
All right. I think we can take maybe, we have a couple of more minutes, Jeroen, so one more question, hopefully. Joe Abley is asking, I think the Internet Watch Foundation takes a similar approach of using hashes to help identify the actual offensive content without exposing people to it. Is there an overlap between what they do and what you are describing?
Yes, there might be. There's also an overlap with, of course, safe browsing that Google provides as a service towards all the browser vendors. And there, the advantage is if you block in DNS, as I said, you might want to do just an NX domain, which means like you don't get an answer, but the user also doesn't know why it is well broken. If you do a walled garden approach, you will get an SSL error most likely nowadays. And if you do the safe browsing version, if you do the blocking in that level, at least the advantage is that you get a notification, a big red screen with an explanation like this is blocked by service XYZ, which is a better approach in my opinion. But yeah, in the end, if we're talking about blocking things, it could just be that the people who want to access certain content, they can, of course, always circumvent. You can use the DNS server from a provider which is not included in the law. For instance, in Switzerland, internet access providers only have to do it. But for instance, Google doesn't because they're not a Swiss internet access provider. Or you can just use a VPN, or you can use Tor, and you can circumvent these lists anyway. So it is primarily useful for accidental going to those locations, I would say.
I think we are just on time, Jeroen, with these last questions. We have a couple of questions more, but they can be taken up on the workshop channel. For now, thank you very much for that presentation. Next up, we have Ulrich Wisser, and he's going to give a lightning talk about .NU's transition from NSEC 3 to NSEC. On to you, Ulrich.
Okay, great. So my name is Ulrich, and I work for the Swedish Internet Foundation for the DNS Labs. And I have been a developer for a registry system, and I'm a part of the center team for the Center Tech Workshop and for the DNS-over Program Committee. And so the Swedish Internet Foundation took over the running of .NU in 2013. And at the time, we didn't want to change a lot of the technical stuff behind it. So we just ran with how it always had been run. And so we continued with NSEC 3. And yes, so then we always had the idea of going to NSEC, but you know, how you do that. And well, when you read the RFC, it seems quite easy. You remove all the NSEC3 records, you put in NSEC records, and you're done. And then I started to talk to people at conferences, and everybody said, yeah, that's how you should do it. But nobody had actually done it. So, and yeah, what could possibly go wrong, you know, and everybody says it should work. And yeah, what could possibly go wrong is a really bad answer if you have to talk for PTS is our regulator in Sweden, and we have the NIS directive. I have my CEO and CISO to answer to, and I need to give them a little bit more answer than, you know, the RFC says it should work. So we had to do some testing. And the first problem with testing NSEC is that NSEC really says there is no answer. So, but you want the answer that there is no answer, not just no answer. And that, of course, you realize that, yeah, there's some really thinking to go on to do this. And so I wrote a little software that basically proxied DNS answers from different servers and mixed NSEC and NSEC3 answers. And yeah, I did test it with the public resolvers from this list, and I can tell you that yeah, really nothing interesting came out of this. The most interesting numbers that we got from this is these where I intentionally destroyed the answers. You know, the NSEC answer doesn't cover the label, or we mix NSEC and NSEC3, and one of them covers the label, but the other doesn't. And you know, I mean, that's really no serious DNS answers. And yeah, the resolvers still handled it quite well. So, so with that said, it really looked good. And so we did a test run. We took the .nu zone and we named it to nutest.nu and did the usual signing that we do with OpenDNSSEC and using an Anycast provider to, you know, distribute the zone. And then we did a measurement with 500 Web Atlas probes. And it looks really, you know, like it's supposed to look. You get mostly NX domain answers, and some resolvers answer no error, which is, you know, quite uneventful. And you see the lines down here. A lot of them just not DNSSEC enabled, and the ones that are, they just change from NSEC3 to NSEC. But everything is really like it should be. And that's when we went live. So with that, you know, we said, okay, we're good to go. Let's do it. And so we did the same thing for .nu. We have 3 Anycast providers for the .nu zone. And this time we did the measurement with 5,000 Web Atlas probes. And yeah, we got this. And it looks a little bit different. And so I just would like to take some time to go over this. And so you see I mean, of course, we get NX domain mostly, and that is because, I mean, we're obviously asking for non-existent domain names. And then we get this no error answers, which is a bit strange, but, you know, not, you know, but we don't get any serve fail, and that is good. So, but you see, when we at the time where the zone went live with the NSEC records instead of NSEC3, there's this huge amount of resolvers that suddenly start to support NSEC but didn't support NSEC3. And that was really a mystery to me, because I mean, nothing of this happened in our trial run. And it turns out that, yeah, I made a kind of a rookie mistake. I instructed the Web Atlas probes to use 512 bytes. And yeah, that's what you get. I still don't understand why the resolvers would answer no error instead of NX domain, but that's what happened. And so we have a huge number of resolvers that support DNSSEC and that validate. And I think the most of the answers that did the no NSEC in the beginning was just, they got the TC bit set. So there were no NSEC records in the answers, but the resolvers actually would have done the NSEC validation. And with that, I'm actually at the end of my presentation. Well, the success. We got no angry customers calling, and everything validation went fine. So yep, we changed the NU zone from NSEC 3 to NSEC. Thank you.
Thanks, Ulrich, for the presentation. At this time, I would like to remind everybody to fill the poll, which should pop up on your screen in a few minutes. I don't have any questions in the Q&A, and one question. We have one question from Dimitri. He's asking, oh no, it's not a question for, it's saying couldn't log into Mattermost. For some reason, I think they couldn't ask their question. Dimitri, do you have a question? Yeah, I'm allowing Dimitri to speak. Yeah, Dimitri, please go ahead and unmute yourself.
I'm done. Thanks. Am I clear?
Yes, I can hear.
Okay, great. Thanks for the work. Just for the record, you're right to be the first on this transition, but we did NSEC 3 opt out to NSEC 3 plain, and that was fun too. We should probably done the same test. So congrats. I guess we should both, pat ourselves on the back. Thanks for your exhaustive testing in the lab. I applaud your diligence. I guess the question is, would you mind telling us the reason of the transition, and do you ever plan to roll it back to NSEC 3 just to see again how the world would change, maybe in a couple of years? I mean, well, NSEC 3 is better, right? There is always support for NSEC 3, though, is definitely not there. So I'm out. Thanks.
Yes. Yeah. So the reason for why we wanted to change is that in the last few years there were several CCTLDs in Europe that had problems with the NSEC 3 chain, and then we actually publish our zone files. If you go to zonedata.iis.se, you can download, you get instructions how you can get the .se zone and the .nu zone. And so we really have no need for NSEC 3.
Yeah, so very unusual.
Yes, and so that given with the failures that other TLDs had, and that we don't have any use for NSEC 3, it seemed more like a liability than a feature.
Great, thank you.
Thank you.
Thanks, Ulrich. We have one question from Brett. Brett, could you please unmute yourself?
Yeah, thank you. Ulrich, one of the reasons that we continue to use NSEC 3 is because of the opt-out and the fact that it doesn't explode the size of the zones. And if you're dealing with large zones, that's actually quite useful. I don't know what the size of the .nu zone is. Was that a consideration at all?
No, we didn't use opt-out before, and we're running the .se zone with the NSEC already, and so the .se zone is 1.4 million domains, and .nu is 450,000 something. So we weren't really concerned about the zone size.
Okay, thank you.
Thanks, Brett. Thanks, Ulrich. We are just about done with all the questions. I don't see any new questions from panelists, attendees, or in the Q&A section. So I think we are done with the presentation.
Good. Thank you very much.
And I would like to thank all the presenters once again for the wonderful presentations. And now I'll hand over to Keith Mitchell.
Okay, thank you, Pallavi, and thank you, Jan, for timekeeping. I think that was a session went really well. Just wanted to do a few admin things to wrap up for the day. Thank you to all the speakers. Both the program committee and the speakers appreciate feedback. It looks as though we've had good engagement with the Zoom polls. So thank you all for clicking on the button in the Q&A window. We'd quite like feedback on the feedback mechanism as well. There is a general feedback survey, which we appreciate your feedback. Your feedback on meeting logistics and how it all went at the OARC34 survey link there. We will very shortly for the next hour be starting the social event. That is in the same Zoom room as the lunchtime break. There was a few people there. Again, there's a short link for that, or the meeting ID is there, and the PIN is 846907. And we will be restarting tomorrow at 1600 UTC, but for that use the same workshop link as you used today. So you probably received a reminder of that. I just wanted to comment about the members only session at the end of tomorrow's proceedings. OARC members who registered for OARC34 and OARC members who requested a link should have received that invite by 1700 today. If you didn't receive that, then please, before 8 AM UTC tomorrow, please let us know, and that will be a confidential session. So that's pretty much it. The one thing that just remains to say is thank you to all our speakers today for their excellent efforts and keeping on time, and all their also contribution towards the rehearsals, which I think have paid off really well. And also thank you to Farsight as our workshop sponsor. That is all I have to say today. I will see you in the social room shortly, and if you don't make the social, see you first thing tomorrow.